Understanding unique numbers and their constraints. Definition of unique numbers. A unique number is defined as a number that is distinct from all others in a given context. This uniqueness can apply to various fields such as databases, mathematics, and real-world identifiers. In databases, a unique constraint ensures that no two rows have the same value for a specified column or combination of columns, thereby maintaining data integrity. 4.8. Examples in real-life identification numbers. Every citizen may have a unique identification number, like a social security number, that distinguishes them from others. Animal identification. In agriculture, each animal in a herd may be assigned a unique number to track health and ownership one. Database management. In databases, a unique constraint is applied to ensure that entries like email addresses or usernames are not duplicated within the system. 4.8. The concept of uniqueness in mathematics. In mathematics, the concept of uniqueness often refers to properties that define specific numbers. For example, the number 1 is unique because it is the multiplicative identity. Multiplying any number by 1 yields the same number. Each whole number is inherently unique. No two different whole numbers can be the same. Unique digits. In the context of digit uniqueness, a number with unique digits means that no digit appears more than once. For instance, the number 123 has unique digits, while 112 does not. 3. Conclusion. The uniqueness constraint is fundamental across various domains, ensuring that entities are distinctly identifiable. Whether through identification numbers in real life or mathematical properties, the principle of uniqueness serves to maintain order and clarity in systems where differentiation is crucial. The concept of all numbers. Originating from 1, the idea that all numbers can be traced back to the number 1 is a fascinating concept in mathematics and philosophy. Let's explore this idea further. The mathematical foundation. In mathematics, particularly in number theory, the number 1 is often considered the building block of all integers. Here's how it works. Counting numbers. The natural numbers, 1, 2, 3, begin with 1. Each subsequent number is formed by adding 1 to the previous number. Multiplication and addition. All integers can be derived from repeated addition of 1. For example, 2 equals 1 plus 1, 3 equal sign 1 plus 1 plus 1, 0, and negative numbers. While 0, 0 and negative numbers, minus 1, minus 2, may seem to deviate from this idea, they can also be conceptualized through the lens of 1. 0 can be viewed as the absence of any units of 1. Negative numbers can be seen as moving backward from 0 in increments of minus 1. Philosophical perspective. From a philosophical standpoint, the idea that all numbers stem from 1 can symbolize unity and singularity, unity and diversity. Just as all numbers can be derived from the single unit of 1, many concepts in life can emerge from a fundamental idea or principle. The origin of existence. In various philosophical traditions, the notion of everything originating from a single source is prevalent. For example, in some interpretations of creation myths, everything comes from a singular entity or force. Applications in real life. The principle that all numbers derive from 1 has practical implications in various fields. Computer science. In binary code, which underlies all digital computing, the basic units are bits represented as either 0 or 1. All complex data structures and computations are built upon these fundamental units. Economics. In economic models, 1 unit, like $1, can represent value and lead to larger sums through transactions and investments. Conclusion. The notion that all numbers originate from 1 highlights the interconnectedness of numerical systems and their foundational principles. This concept not only enriches our understanding of mathematics, but also invites deeper reflections on unity and origin across various domains of knowledge. Whether through counting, philosophical inquiry, or practical applications, the significance of the number 1 remains profound and far-reaching, exploring the relationships and patterns in numbers. Your exploration of numbers and their relationships is intriguing. Let's break down the concepts you've presented and analyze the connections step by step. Basic foundations. You started with fundamental equations. 1 equals 1 times 1, 2 equals 1 plus 1. This establishes a foundation where all numbers can be derived from 1 through basic arithmetic operations. Concatenation of numbers. You mentioned concatenating numbers, which means joining them together to form new numbers. Concatenating 1 and 2, 12, 12. You then related this to multiplication. 12 equals 3 times 4. This is correct since 3, 4, 1, 2, 3 is 4 plus 9, 12. Further concatenation. Next, you concatenated 12, 12 and 3,434. Concatenating 12 and 34. 1, 2, 3, 4, 1, 2, 3, 4. You then express this as the sum of its digits. 1 plus 2 plus 3 plus 4 equals 10. This is a valid calculation. Exploring factorials and squares. You connected 10, 10 to other mathematical concepts. 10 equals 5 times 2, 52, equal sign 25. You also noted that 42 plus 32 equal sign 16 plus 9 equal sign 2,542 plus 32 equal sign 16 plus 9 equal sign 25, which is correct. Pythagorean triplets, you mentioned the triplet 5, 4, 35, 4, 3, the triplet 3, 4, 5, 3, 4, 5. Is indeed a Pythagorean triplet since 32 plus 42 equal sign 5,232 plus 42 equal sign 52. Concatenation of results. You concatenated 12, 12 and 5, 4, 3, 5, 4, 3. Concatenating 12, 12 and 5, 4, 3, 5, 4, 3 gives 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Then you calculated the factorial of 55, 5. Equal sign 120. This is accurate since 5. Added 5, 4, 3, 2, 1, 205, 5, 4, 3, 2, 2, 1, 20. Symmetry and further connections. You noted 120 equals sign 12 plus 0 equals 12. This represents a symmetry where you simplified back to 12, 12. Then you shifted to another sequence. 21 equals 3 times 7. This is also correct since 300 2, 3, 7 out 2 to 1. You concluded with 37 equals 3 plus 7 equals sign 10. This sums correctly. Conclusion. Your exploration illustrates a fascinating interplay of arithmetic operations, concatenation, and properties of numbers, including Pythagorean triplets and factorials. The connections you've drawn show how numbers can be manipulated and related in various ways, revealing deeper mathematical relationships. If you're interested in further exploring these concepts or any specific area of mathematics, feel free to ask. Continuing the exploration of number relationships. Let's delve deeper into the fascinating relationships and patterns you've established, expanding on the concepts of concatenation, arithmetic operations, and their implications in mathematics. Further, concatenation and patterns. You have already shown how concatenating numbers leads to new values. Let's explore this concept further by examining additional concatenated sequences and their properties. Example, concatenating larger sequences. Concatenate 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This number can be broken down into its digits. 1 plus 2 plus 3 plus 4 plus 5 equals 15. This sum can also be related to multiplication. 15 equals 3 times 5 or 15 equals 5 times 3. Exploring factorials. Further factorials are a powerful mathematical tool. Let's explore how they relate to the sums and products we've discussed. 6. Equal sign 720. The sum of the digits in 720 is 7 plus 2 plus 0 equals 9. This can lead to interesting patterns with other factorials. 5. Equal sign 120, where the sum of the digits is 1 plus 2 plus 0 equals 3. Symmetry and palindromic numbers. You mentioned symmetry in your previous calculations. This can also lead us to explore palindromic numbers, numbers that read the same forwards and backwards. Examples of palindromic numbers: 121, 13, 31, 1, 2, 3, 2, 1. These numbers exhibit symmetry, which can be visually appealing and mathematically interesting. Exploring Pythagorean triplets further. You referenced Pythagorean triplets like 3, 4, 53, 4, 5. Let's look at some other well-known triplets. 5, 12, 13. Here, 52 plus 122 equals sign 25 plus 144 equals sign 169 equals sign 13,252 plus 122 equals sign 25 plus 144 equals sign 169 equals sign 132. 8, 15, 17. 82 plus 152 equals sign 64 plus 225 equals sign 289 equals sign 17,282 plus 152 equals sign 64 plus 225 equals sign 289 equals sign 172. These triplets can be generated using formulas or found through various methods in number theory, exploring number properties even and odd. The numbers you've worked with can also be classified into even and odd. Even numbers, numbers divisible by 22, for example, 2, 4, 62, 4, 6. Odd numbers, numbers not divisible by 22, for example, 1, 3, 51, 3, 5. Example, in your concatenated sequences, the number 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 has 3 odd digits, 1, 3, and 5, and 2 even digits, 2 and 4. Conclusion. The exploration of numbers through concatenation, factorial symmetry, Pythagorean triplets, and classifications into even and odd provides a rich tapestry of mathematical relationships. Each concept opens doors to further inquiries and deeper understanding of numerical properties. If you'd like to continue exploring specific areas such as advanced number theory concepts or applications in real-world scenarios, please let me know. Continuing the exploration of number relationships. Let's delve even deeper into the fascinating world of numbers, exploring advanced concepts and additional patterns that emerge from your previous observations. Advanced concatenation and patterns. We can expand our exploration of concatenation by looking at more complex sequences and their properties. Example, concatenating multiple sequences. Consider concatenating the first 5 natural numbers and analyzing their properties. Concatenate 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Now, let's concatenate the next set of numbers. Concatenate 6, 7, 8, 9, 10, 6, 7, 8, 9, 1, 0, 6, 7, 8, 9, 1, 0. Analyzing the results, sum of digits in each concatenated number for 1, 2, 3, 4, 5, 1 plus 2 plus 3 plus 4 plus 5 equals sign 151 plus 2 plus 3 plus 4 plus 5 equals sign 15 for 6, 7, 8, 9, 1, 0, 6 plus 7 plus 8 plus 9 plus 1 plus 0 equals sign 316 plus 7 plus 8 plus 9 plus 1 plus 0 equals sign 31. These sums can be further analyzed for patterns or relationships, exploring Fibonacci numbers. The Fibonacci sequence is another fascinating area of number theory. The sequence starts with 0 and 1, and each subsequent number is the sum of the 2 preceding ones. Fibonacci sequence 0, 1, 1, 2, 3, 5, 8, 13, 21. 0, 1, 1, 2, 3, 5, 8, 13, 21. Properties of Fibonacci numbers golden ratio. As you progress through the Fibonacci sequence, the ratio between consecutive Fibonacci numbers approaches the golden ratio, approximately 1.6180339887, 1.6180339887. Sum of Fibonacci numbers. The sum of the first nn Fibonacci numbers is equal to the n plus 2b, n plus 2 the Fibonacci number minus 1. For example, f0 plus f1 plus f2 plus f3 equals sign f5, 1f0 plus f1 plus f2 plus f3 equals sign f5, 1 0 plus 1 plus 1 plus 2 equals sign 3 equals sign f5, 10 down plus 1 plus 2, 3 takes f5, and 1 exploring prime numbers. Prime numbers are another captivating area of study. A prime number is a natural number greater than one that cannot be formed by multiplying 2 smaller natural numbers. Examples of prime numbers, the first few primes are 2, 3, 5, 7, 11, 13. Properties of prime numbers distribution. Primes become less frequent as numbers increase but are distributed in a way that mathematicians study extensively, for example, the prime number theorem. Applications. Primes are crucial in cryptography and computer security. Exploring modular arithmetic. Modular arithmetic is a system of arithmetic for integers where numbers wrap around after reaching a certain value, the modulus. Example, in modulo 1010, 12 mod 10 equals sign 212 mod 10 equals sign 225 mod 10 equals sign 525 mod 10 equals sign 5. This concept is useful in various applications such as clock arithmetic and cryptography. Conclusion. The exploration of advanced concepts such as concatenation patterns, Fibonacci numbers, prime numbers, and modular arithmetic reveals a rich landscape within mathematics. Each area has its own unique properties and applications that contribute to a deeper understanding of numerical relationships. But if you have specific areas you want to dive into further, such as applications in real-world contexts or deeper theoretical explorations, please let me know. Further exploration of number concepts. Let's continue our journey through the fascinating world of numbers by exploring additional mathematical concepts, relationships, and applications. We'll delve into topics such as sequences, number theory, combinatorics, and more. Exploring sequences and series are fundamental concepts in mathematics that involve ordered lists of numbers and their sums. Arithmetic sequences. An arithmetic sequence is a sequence of numbers in which the difference between consecutive terms is constant. Example, the sequence 2, 5, 8, 11, 8.2, 5, 8, 11 has a common difference of 3. The nth term of an arithmetic sequence can be expressed as an equal sign, a 1 plus n1 dan desar a1 pluses n1 d, where a1 is the first term and dd is the common difference. Geometric sequences. A geometric sequence is a sequence where each term after the first is found by multiplying the previous term by a fixed non-zero number called the common ratio. Example, the sequence 3, 6, 12, 24.3, 6, 12, 24 has a common ratio of 2. The nth term of a geometric sequence can be expressed as nr, n1, and 8a1r, n1, where RR is the common ratio. Exploring factorials and combinatorics. Factorials are not only useful in arithmetic but also play a significant role in combinatorics, which is the study of counting, arrangement, and combination. Factorial notation. The factorial of a non-negative integer nn is denoted as nnn and defined as nx, ny1, x, n2, x, x3, x2, x1, nx, n1, x, n2, x, x3, 2x1 with 0, equals sign 10, equals sign 1. Combinations and permutations. Permutations refer to the arrangement of objects where order matters. The number of ways to arrange nn objects is given by n. Combinations refer to the selection of objects where order does not matter. The number of ways to choose RR objects from nn objects is given by C n and R, n R, n R R, C D R, R R, n R M. Exploring number theory. Number theory studies the properties and relationships of numbers, particularly integers. Divisibility rules. Understanding divisibility rules can help identify factors and multiples. A number is divisible by 2 if its last digit is even. A number is divisible by 3 if the sum of its digits is divisible by 3. A number is divisible by 5 if its last digit is 0 or 5. Prime factorization. Every integer greater than 1 can be uniquely expressed as a product of prime numbers. This is known as its prime factorization. For example, the prime factorization of 28 is 22 to 1. Exploring symmetry and patterns. Mathematics often reveals symmetry and patterns that can be visually represented or analyzed. Palindromic numbers. As previously mentioned, palindromic numbers read the same forwards and backwards. They exhibit symmetry that can be interesting to explore. Examples: 121, 13, 31, 1, 2, 3, 2, 1, 1, 2, 1, 13, 31, 1, 2, 3, 2, 1. Symmetrical patterns in geometry. In geometry, symmetry plays a crucial role. Shapes can exhibit reflective symmetry, mirror images, rotational symmetry, same appearance after rotation, and translational symmetry, repeating patterns. Conclusion. The exploration of sequences, combinatorics, number theory, and symmetry provides deeper insights into the structure and relationships within mathematics. Each topic opens up new avenues for understanding how numbers interact and how they can be applied in various fields. If you have specific areas you'd like to explore further, such as applications in science or technology or deeper dives into particular mathematical theories, please let me know. Continuing the exploration of mathematical concepts, let's delve deeper into additional mathematical concepts and their applications, exploring areas such as advanced number theory, combinatorial designs, mathematical patterns, and real-world applications of these principles. Advanced number theory. Number theory is a rich field with many interesting subtopics. Here are a few advanced concepts. Modular arithmetic. Modular arithmetic deals with integers and their remainders when divided by a fixed number, the modulus. It's widely used in computer science, cryptography, and coding theory. Example: in modulo 7, the numbers cycle every 7. 10 mod 7 equals sign 310 mod 7 equals sign 315 mod 7 equals sign 115 mod 7 equals sign 1. Diophantine equations. These are polynomial equations that seek integer solutions. A classic example is the equation ax plus by equals sign, cax plus by equals sign c, where a, b, and c are integers. Solutions exist if and only if the greatest common divisor, GCD of a and b, divides c. Combinatorial design. Combinatorial design is a branch of combinatorics that deals with the arrangement of elements into specific configurations. Block designs. A block design is a collection of subsets, blocks, of a finite set such that certain conditions are met. One common type is the balanced incomplete block design, BRBD, used in statistical experiments. Example, if you have a set of items you want to test in groups, BRBDs help ensure that each item appears in a balanced way across different groups. Mathematical patterns. Mathematics is filled with patterns that can be observed in sequences, shapes, and numbers. Fibonacci sequence in nature. The Fibonacci sequence appears frequently in nature, such as in the arrangement of leaves on a stem, the branching of trees, or the arrangement of seeds in a sunflower. The ratio of successive Fibonacci numbers approaches the golden ratio, approximately 1.618, which is often associated with aesthetics in art and architecture. Pascal's triangle is a triangular array where each number is the sum of the two directly above it. It has numerous applications in algebra, probability, and combinatorics. The nth row corresponds to the coefficients in the binomial expansion. A plus b, n, a, k, so n, c, n, k, n, k, a plus b, n, k, row 1, c, n, k, and kbk real-world applications. Mathematical concepts have practical applications across various fields. Cryptography number theory plays a crucial role in modern cryptography. For example, RSA algorithm, this widely used encryption method relies on the difficulty of factoring large prime numbers. Computer science algorithms often utilize combinatorial principles for efficient data processing and optimization problems. Sorting algorithms. Many algorithms, like quicksort or merge sort, rely on combinatorial techniques to manage data efficiently. Exploring graph theory. Graph theory studies graphs, which are mathematical structures used to model pairwise relations between objects. Basic concepts: vertices and edges. A graph consists of vertices, nodes connected by edges, lines. Types of graphs: directed graphs, where edges have a direction. Undirected graphs, where edges do not have a direction. Applications of graph theory: network analysis, used in social networks, transportation systems, and communication networks. Pathfinding algorithms. Algorithms like Dijkstra's or A** are used to find the shortest path in weighted graphs, applicable in GPS navigation systems. Conclusion. The exploration of advanced number theory, combinatorial designs, mathematical patterns, and their real-world applications reveals the depth and richness of mathematics. Each concept not only enhances our understanding, but also demonstrates how mathematics underpins various fields from technology to nature. If there are specific topics or applications you would like to explore further, such as deeper dives into graph theory or practical uses in science, please let me know. Further exploration of mathematical concepts and applications. Let's continue our journey through mathematics by diving into more advanced topics, exploring their implications, and discovering how they connect to real-world scenarios. We'll cover topics such as mathematical logic, topology, chaos theory, and their applications in various fields. Mathematical logic. Mathematical logic is a subfield of mathematics that uses formal logical systems to study the nature of mathematical reasoning. Propositional logic. Propositional logic deals with propositions that can be either true or false. Key concepts include logical connectives and true if both propositions are true, or true if at least one proposition is true. Not inverts the truth value of a proposition. Truth tables, used to determine the truth values of logical expressions. Predicate logic. Predicate logic extends propositional logic by including quantifiers. Universal quantifier indicates that a statement is true for all elements in a domain. Existential quantifier indicates that there exists at least one element in a domain for which the statement is true. Topology is the study of properties that remain invariant under continuous transformations. It focuses on the qualitative aspects of space rather than quantitative measurements. Basic concepts. Topological spaces, a set equipped with a topology which defines open sets and allows for the generalization of concepts like convergence and continuity. Homeomorphism, a continuous function between two topological spaces that has a continuous inverse. If two spaces are homeomorphic, they're considered topologically equivalent. Applications of topology data analysis. Topological data analysis, TDA, uses concepts from topology to study the shape of data and extract meaningful insights. Robotics topology helps in motion planning and understanding configuration spaces. Chaos theory. Chaos theory studies complex systems that are highly sensitive to initial conditions, leading to seemingly random behavior despite being deterministic. Key concepts. Sensitivity to initial conditions, often illustrated by the butterfly effect, where small changes in initial conditions can lead to vastly different outcomes. Strange attractors. Patterns that emerge in chaotic systems, representing stable states toward which a system tends to evolve over time. Applications of chaos theory, weather forecasting. Chaos theory plays a crucial role in understanding and predicting weather patterns due to the complex interactions within the atmosphere. Economic models can exhibit chaotic behavior, influencing market predictions and financial strategies. Fractals. Fractals are complex geometric shapes that can be split into parts, each of which is a reduced scale copy of the whole, a property known as self-similarity. Characteristics of fractals: infinite complexity. Fractals exhibit detail at every scale. Zooming in reveals more structure. Non-integer dimensions. Fractals often have dimensions that are not whole numbers, indicating their complexity. Examples of fractals: Mandelbrot set, a famous fractal defined by a simple iterative process showcasing intricate boundary structures. Koch snowflake, a curve that increases its perimeter infinitely while enclosing a finite area. Applications of fractals: computer graphics. Fractal algorithms are used to create realistic landscapes and textures in digital art and simulations. Nature modeling. Fractals model natural phenomena such as coastlines, clouds, and mountain ranges due to their self-similar properties. Real-world applications of mathematics. Mathematics is not just an abstract discipline, it has profound implications across various fields. Engineering mathematics is essential in engineering disciplines for modeling systems, analyzing structures, and optimizing designs. Techniques such as calculus and differential equations are fundamental in fields like civil and mechanical engineering. Medicine statistics and probability play critical roles in medical research, particularly in clinical trials where they help determine the efficacy of treatments and interventions. Computer science algorithms based on mathematical principles drive computer science innovations, from data structures to artificial intelligence. Concepts like graph theory underlie network design and optimization problems. Conclusion: the exploration of mathematical logic, topology, chaos theory, fractals, and their real-world applications highlights the breadth and depth of mathematics as a discipline. Each topic opens new avenues for understanding complex systems and solving practical problems across various fields. If you have specific areas you would like to explore further, such as applications in artificial intelligence or deeper dives into any particular mathematical theory, please let me know. Epilogue. As we conclude our exploration of advanced mathematical concepts and their applications, it is essential to reflect on the journey we have undertaken and the path that lies ahead for mathematics education. The insights gained throughout this book highlight the critical role that mathematics plays in shaping our understanding of the world and addressing the challenges we face as a society. The evolving landscape of mathematics education. The landscape of mathematics education is undergoing significant transformation, driven by technological advancements and a growing recognition of the need for innovative teaching methods. Traditional approaches that emphasize rote memorization and procedural tasks are giving way to more dynamic and interactive learning experiences. With the rise of digital technologies, educators now have access to a plethora of resources that can enhance student engagement and foster a deeper understanding of mathematical concepts. Online platforms, adaptive learning tools, and interactive simulations allow students to explore mathematics in ways that were previously unimaginable. By integrating these technologies into the classroom, educators can create an environment that nurtures inquiry, creativity, and critical thinking, addressing the mathematics crisis. Despite these advancements, challenges remain. Recent assessments have revealed alarming statistics regarding students' proficiency in mathematics, particularly in critical years of education. The COVID-19 pandemic has exacerbated existing disparities, highlighting the urgent need for effective interventions to support students who may be falling behind. To address this crisis, it is imperative for educators to adopt innovative approaches that connect mathematical concepts to real-world applications. By demonstrating the relevance of mathematics in everyday life, whether through practical examples or interdisciplinary projects, teachers can cultivate a positive attitude toward math among students. Encouraging students to see mathematics not just as a subject confined to textbooks, but as a vital tool for problem solving in various contexts will foster greater interest and motivation. The role of collaboration among educators, policymakers, parents, and communities is essential for advancing mathematics education. By working together, stakeholders can develop comprehensive strategies that prioritize equitable access to quality educational resources. This collaboration should extend beyond traditional boundaries, incorporating insights from various disciplines to enrich the learning experience. Professional development opportunities for teachers are crucial in equipping them with the skills needed to implement innovative practices effectively. Ongoing training in emerging technologies and pedagogical strategies will empower educators to create engaging learning environments that inspire students to excel in mathematics. Looking ahead, as we look to the future, it is clear that mathematics will continue to play a pivotal role in addressing global challenges, from climate change and public health crises to economic disparities and technological advancements. The ability to think mathematically will be essential for individuals seeking to navigate an increasingly complex world. By fostering a culture that values mathematical literacy and critical thinking, we can prepare future generations to tackle these challenges with confidence and creativity. Mathematics is not merely a subject. It is a powerful tool for understanding the world and driving positive change. Final thoughts. In closing, this book serves as both a celebration of the beauty and significance of mathematics and a call to action for educators and stakeholders alike. Let us commit ourselves to nurturing a love for mathematics in our students while equipping them with the skills they need to thrive in an ever-evolving landscape. Together we can pave the way for a brighter future where mathematics empowers individuals and transforms societies. This epilogue encapsulates the key themes discussed throughout the book while emphasizing the importance of innovation in mathematics education and collaboration among stakeholders. If you would like any modifications or additional points included in this epilogue, or if you need further assistance with any other aspect of your project, please let me know. Introduction. Mathematics is often seen as a challenging subject, yet it is an essential tool that shapes our understanding of the world around us. It provides the language and framework for analyzing patterns, making predictions and solving complex problems. From its foundational concepts to advanced theories, mathematics plays a crucial role in various disciplines, including science, engineering, economics, and social sciences. In this book, Advanced Mathematical Concepts and Their Applications, we embark on a journey to explore the rich landscape of mathematics. We will delve into key concepts such as linear algebra, calculus, statistics, and graph theory, examining their significance and real-world applications. By understanding these advanced topics, readers will not only enhance their mathematical literacy, but also appreciate the profound impact of mathematics on everyday life. The relevance of advanced mathematics. The relevance of advanced mathematics extends far beyond theoretical pursuits. It is deeply intertwined with technological advancements and scientific discoveries. For instance, data science. In an era defined by big data, mathematical techniques are employed to extract insights from vast datasets. Statistical analysis and machine learning algorithms rely on mathematical principles to make sense of complex information. Engineering. Mathematics is the backbone of engineering disciplines. It enables engineers to model physical systems, optimize designs, and ensure safety and efficiency in structures and machines. Economics. Mathematical models are used to analyze economic behavior, forecast market trends, and inform policy decisions. Understanding mathematical concepts allows economists to quantify relationships between variables and assess the impact of changes in policy or market conditions. Bridging theory and practice. While mastering advanced mathematical concepts is essential for academic success, it is equally important to bridge the gap between theory and practice. This book emphasizes practical applications of mathematics in various fields, real-world problem solving. Each chapter will include case studies and examples that demonstrate how mathematical concepts are applied to solve real-world problems. By connecting theory with practice, readers will gain a deeper understanding of the relevance of mathematics in their lives. Interdisciplinary connections. Mathematics intersects with numerous disciplines. We will explore how mathematical principles contribute to advancements in fields such as computer science, biology, environmental science, and finance. This interdisciplinary approach highlights the versatility of mathematics as a problem-solving tool. Fostering a growth mindset. As we embark on this exploration of advanced mathematics, it is essential to foster a growth mindset, an attitude that embraces challenges and views failures as opportunities for learning. Mathematics can be daunting for many students. However, with perseverance and practice, anyone can develop their mathematical skills. This book aims to provide a supportive framework for learners at all levels. Whether you are a student seeking to strengthen your understanding of advanced concepts or a professional looking to apply mathematics in your field, you will find valuable insights and resources throughout these pages. Conclusion. In conclusion, advanced mathematical concepts and their applications serves as both an introduction to key mathematical ideas and a guide for applying these concepts in practical contexts. As we delve into each chapter, we invite you to engage with the material actively, solving problems, exploring applications, and appreciating the beauty of mathematics. Together, let us unlock the potential of advanced mathematics and discover its power to transform our understanding of the world. This introduction sets the stage for exploring advanced mathematical concepts while emphasizing their relevance and applications in various fields. If you would like any adjustments or additional content included in this introduction, or if you need further assistance with any other aspect of your project, please let me know. Continuing the exploration of mathematics in the Quran, the intersection of mathematics and Quranic teachings. The Quran, as a foundational text of Islam, not only provides spiritual guidance, but also encourages the pursuit of knowledge, including mathematics. This intersection between mathematics and religious teachings has led to significant developments in mathematical thought, particularly during the medieval Islamic period. Scholars have explored various mathematical concepts embedded within the Quran, revealing a rich tapestry of numerical significance that underscores its divine authorship. Mathematical phenomena in the Quran, gematria and abjad numerals. One of the intriguing aspects of mathematical analysis in the Quran is the use of gematria, specifically through abjad numerals. This system assigns numerical values to Arabic letters, allowing for a deeper exploration of the text structure. Studies have shown that these numerical values can reveal patterns and constants, such as the Quran constant, QC, which has been found to relate closely to the golden ratio, approximately 1.618. This connection suggests a deliberate mathematical design within the Quran that emphasizes its authenticity and divine origin. Statistical analysis. Researchers have conducted statistical analyses on the Quran structure, examining the total number of words, verses, and chapters. These analyses have uncovered elegant mathematical equations that accurately determine these statistics, further supporting claims of a sophisticated design. 17. Mathematical equations. The Quran contains references to various mathematical domains, including arithmetic, geometry, and algebra. For instance, verses discussing inheritance laws necessitate an understanding of basic arithmetic and algebraic principles. These principles have historically compelled Muslim scholars to develop advanced mathematical concepts to address practical needs in religious observance and daily life. 2.5. Historical context. Mathematics in Islamic civilization. The medieval Islamic world was a crucible for mathematical innovation. Scholars like Muhammad ibn Musa al-Khwarizmi laid the groundwork for algebra as a distinct field, influencing both Islamic and Western mathematics. His work emphasized systematic approaches to solving equations and introduced methods still used today. 6. Algebraic foundations. Al-Khwarizmi's contributions included techniques for solving linear and quadratic equations, which were essential for practical applications such as trade and inheritance calculations. Geometry and astronomy. The need for precise measurements in architecture and navigation led to advancements in geometry and trigonometry during this period. The Quranic emphasis on observation and reasoning further spurred these developments. 4. Contemporary relevance. The relevance of mathematics within the Quran continues to resonate today. As modern scholars investigate these mathematical phenomena, they find that they align with contemporary scientific principles. This ongoing exploration not only enhances our understanding of the Quran, but also fosters a renewed appreciation for mathematics as a universal language. Educational implications. Integrating mathematical concepts found in religious texts can enrich educational curricula, providing students with a holistic understanding of how mathematics intersects with culture, history, and spirituality. Interdisciplinary research. The study of mathematics in religious texts encourages interdisciplinary research that bridges theology, philosophy, history, and mathematics, fostering dialogue among diverse fields. Conclusion. The exploration of mathematics in the Quran reveals profound insights into its structure and significance. Through gematria, statistical analysis, and historical context, we uncover a rich tapestry of numerical phenomena that underscore its divine authorship. As we continue to investigate these connections, we not only enhance our understanding of the Quran, but also reaffirm the importance of mathematics as a critical tool for knowledge across cultures and disciplines. This continuation emphasizes the relationship between mathematics and the teachings found within the Quran, while highlighting historical context and contemporary relevance. If you would like any adjustments or additional content included, or if you need further assistance with any other aspect of your project, please let me know. Practical applications of mathematical concepts found in the Quran. The Quran, as a foundational text of Islam, contains numerous references to mathematical concepts that have practical applications in various aspects of life. These applications are not only relevant for religious observance, but also extend to fields such as science, economics, and daily decision-making. Below are some key areas where mathematical concepts derived from the Quran find practical use. Calculating zakat and ushr zakat, almsgiving, and ushr, a form of agricultural tax, are fundamental aspects of Islamic finance that require precise calculations based on mathematical principles. Zakat calculation. The Quran specifies that Muslims must give a portion, usually 2.5%, of their accumulated wealth annually to those in need. This necessitates an understanding of percentages and financial mathematics to ensure accurate contributions. Ushr calculation. For agricultural produce, ushr is typically calculated as 10% of the harvest if it is irrigated naturally, or 5% if it is irrigated artificially. Farmers must apply these calculations to determine their obligations accurately, determining prayer timings. Mathematics plays a crucial role in determining the timings for the 5 daily prayers. Salah, lunar calendar. The Islamic calendar is lunar-based, and calculations involving the moon's phases are essential for determining the start of each month, including Ramadan and Eid celebrations. Geometric calculations. The direction of prayer, Qibla, requires knowledge of geometry and trigonometry to accurately determine the angle relative to the Kaaba in Mecca from different locations around the world. Inheritance distribution. The Quran provides specific guidelines for inheritance distribution among heirs, which involves complex mathematical calculations. Fractional distribution. The Quran outlines shares for various relatives, for example, parents, spouses, children, using fractions. Understanding how to calculate these fractions is essential for ensuring fair and just distribution according to Islamic law. Astronomy and timekeeping. The Quran references celestial bodies and their movements, which have practical implications for timekeeping and navigation. Lunar calendar regulation. The Quran emphasizes the importance of the lunar calendar for marking months and years, which requires an understanding of cycles and periodic functions. Astronomical calculations. Knowledge of geometry and trigonometry is necessary for calculating celestial positions, which can assist in navigation and determining prayer times. Statistical analysis. The Quran encourages observation and reasoning, which can be linked to statistical methods. Data collection. The principles found in the Quran can guide data collection methods for various purposes, including social research or public health assessments. Analysis of trends. Statistical analysis can help interpret trends related to community welfare based on Quranic teachings about social justice, geometry, and measurement. Mathematical concepts related to geometry are also present in the Quran. Shapes and structures. The Quran discusses various shapes, for example circles, lines, which can be applied in architectural design and construction practices that align with Islamic principles. Measurement standards. Accurate measurements are essential in trade, agriculture, and construction, areas where Islamic teachings emphasize fairness and honesty. Conclusion. The mathematical concepts found in the Quran extend beyond theoretical discussions. They have practical applications that influence various aspects of daily life for Muslims. From financial obligations like zakat to astronomical calculations for prayer times, mathematics serves as a vital tool for fulfilling religious duties while promoting fairness, equity, and social responsibility. By understanding these applications, individuals can better appreciate the profound connection between mathematics and spirituality within the context of Islamic teachings. This section outlines practical applications of mathematical concepts found in the Quran while emphasizing their relevance in everyday life. If you would like any adjustments or additional points included, or if you need further assistance with any other aspect of your project, please let me know. How mathematical concepts in the Quran are used to determine prayer and fasting timings. The Quran provides specific guidelines for the timing of prayers and fasting, which are fundamental components of Islamic practice. These timings are determined through a combination of astronomical observations and mathematical calculations, reflecting the intricate relationship between faith and science. Below, we explore how these mathematical concepts are applied to establish prayer and fasting times. Astronomical phenomena. The determination of prayer times is closely linked to the position of the sun in the sky, which can be quantified using various astronomical measurements. The Quran emphasizes the importance of observing natural phenomena, which aligns with the mathematical methods used to calculate prayer times. Fajr, dawn. The time for Fajr prayer begins at dawn, defined as the moment when the first light appears on the horizon. This is typically calculated when the sun is approximately 20 degrees below the horizon, a measurement that can be determined using trigonometric calculations. Zuhr, noon. Zuhr prayer time starts when the sun has passed its zenith, highest point in the sky, and begins to decline. The exact timing can be calculated based on local solar noon, which varies depending on longitude and latitude, ASR, afternoon. The timing for ASR is determined by the length of an object's shadow. According to different schools of thought, ASR begins when an object's shadow is equal to its length or twice its length. This requires knowledge of geometric principles to measure shadows accurately. Maghrib, sunset. Maghrib prayer time starts immediately after sunset when the sun disappears below the horizon. This can be calculated using precise astronomical observations. Isha, evening. Isha begins when twilight has disappeared, which is typically defined as approximately 1 hour and 50 minutes after sunset, depending on local conditions. Mathematical modeling. Mathematical modeling plays a crucial role in determining accurate prayer times across different geographical locations. Spherical trigonometry. This branch of mathematics is used to calculate angles and distances on a sphere, which is essential for determining solar positions at various latitudes and longitudes. Spherical trigonometric functions help derive equations that predict solar movements throughout the day. Equations of time. These equations account for variations in solar time due to Earth's elliptical orbit and axial tilt. Adjustments based on these calculations ensure that prayer times remain accurate throughout the year. Sun position calculations. By employing algorithms based on latitude, longitude, and date, software applications can compute precise prayer times for any location globally. These calculations often use established formulas derived from astronomical principles. Fasting timings. The timing for fasting during Ramadan also relies on similar astronomical observations. Suhoor, pre-dawn meal. The fast begins at Fajr, which requires precise calculations to determine when dawn occurs based on the aforementioned criteria. Iftar, breaking fast. Iftar occurs immediately after sunset, Maghrib, marking the end of daily fasting. The timing is calculated similarly to Maghrib prayer time. Technological integration. Modern technology has greatly enhanced the accuracy of determining prayer and fasting timings. Mobile applications. Many smartphone applications utilize GPS data along with mathematical algorithms to provide users with real-time prayer timings based on their location. Astronomical software. Programs designed for astronomical calculations can model solar positions accurately, allowing for precise determination of prayer times throughout the year. Conclusion. The mathematical concepts found in the Quran serve as foundational elements for determining prayer and fasting timings within Islamic practice. By integrating astronomy with mathematical modeling, Muslims can ensure that they observe their religious duties at the correct times throughout the day and year. This blend of faith and science not only enriches spiritual practice, but also exemplifies how mathematics can be applied to enhance our understanding of natural phenomena in everyday life. If you have any further questions or need additional information on this topic or related subjects, please let me know. How spherical trigonometry helps in calculating prayer times. Spherical trigonometry is a branch of mathematics that deals with the relationships between angles and distances on the surface of a sphere. This mathematical discipline is particularly useful in determining Islamic prayer times, which are based on the position of the sun in the sky. Here's how spherical trigonometry is applied to calculate these important timings. Understanding solar position. The primary factor in determining prayer times is the position of the sun relative to an observer's location on Earth. Spherical trigonometry provides the tools to calculate solar angles, which are essential for identifying the specific times for each of the 5 daily prayers. Fajr, dawn. The time for Fajr begins at dawn, calculated when the sun is approximately 18 degrees below the horizon. Spherical trigonometry helps determine this angle based on geographical coordinates, latitude and longitude. Zuhr, noon. Zuhr prayer time starts when the sun has passed its zenith. The calculation involves determining local solar noon, which can vary by location and date. ASR, afternoon. The timing for ASR depends on the length of an object's shadow, which is influenced by the sun's angle. Spherical trigonometry is used to calculate this angle and consequently the shadow length. Maghrib, sunset. Maghrib prayer occurs immediately after sunset when the sun dips below the horizon. This timing can be accurately calculated using spherical trigonometric functions. Isha, evening. Isha begins when twilight has disappeared, typically defined as when the sun is about 17 degrees below the horizon. Again, spherical trigonometry aids in calculating this angle. Mathematical modeling. The application of spherical trigonometry involves mathematical modeling that incorporates various factors affecting solar positions. Equations of time. These equations account for variations in solar time due to Earth's elliptical orbit and axial tilt. By integrating these factors into calculations, one can achieve accurate prayer timings throughout the year. Latitude and longitude. The geographical coordinates of a location significantly influence solar angles. Spherical trigonometry allows for precise calculations based on these coordinates, ensuring that prayer times are tailored to specific locations. Solar declination. The angle between rays of sunlight and the plane of the Earth's equator varies throughout the year. This variation is essential for accurately determining prayer times and can be calculated using spherical trigonometric functions. Practical applications. The use of spherical trigonometry in calculating prayer times has practical implications. Software development. Many applications and online tools utilize spherical trigonometric calculations to provide accurate prayer times based on user location. These tools often incorporate algorithms that account for local conditions and astronomical data. Educational tools. Understanding how to apply spherical trigonometry in real-world scenarios enhances educational curricula, allowing students to see practical applications of mathematical concepts. Community engagement, accurate determination of prayer. Times fosters community cohesion by ensuring that congregational prayers occur at appropriate times, enhancing communal worship experiences. Conclusion: spherical trigonometry plays a vital role in calculating Islamic prayer times by providing mathematical frameworks for understanding solar positions relative to Earth. Through precise calculations involving angles, latitude, and solar declination, this branch of mathematics ensures that Muslims can observe their prayers at the correct times throughout the day. As technology continues to advance, integrating spherical trigonometric principles into applications will enhance accessibility and accuracy for practitioners around the world. If you have any further questions or need additional information on this topic or related subjects, please let me know. Spherical trigonometry plays a crucial role in calculating prayer times by accounting for the Earth's curvature and the position of the Sun in relation to specific geographical locations. Here's how spherical trigonometry is applied in this context. Understanding solar position. The determination of prayer times relies on accurately calculating the sun's position at any given time of day. Spherical trigonometry enables this by using the following concepts. Solar declination. This is the angle between the rays of the sun and the plane of the Earth's equator. It varies throughout the year as the Earth orbits around the sun. Spherical trigonometry helps calculate this angle, which is essential for determining when certain prayers should be performed. Hour angle. The hour angle represents the time since solar noon, expressed in angular measurement, degrees. It helps determine how far the sun has moved across the sky from its highest point. Spherical trigonometry equations are used to calculate this angle based on local solar time. Calculating prayer times. Spherical trigonometry provides mathematical models that incorporate various factors affecting solar positions and, consequently, prayer times, Fajr and Isha. The timings for these prayers are determined based on specific angles below the horizon, commonly 18 degrees for Fajr and 17 degrees for Isha. Spherical trigonometric functions calculate these angles to determine when dawn and twilight occur, taking into account the curvature of the Earth. Zuhr. Zuhr prayer time begins when the sun has passed its zenith, highest point. Spherical trigonometry is used to find local solar noon, which varies by location due to Earth's curvature and axial tilt. ASR. The ASR prayer time is determined by measuring shadows cast by objects. The length of shadows changes with the sun's angle, which can be calculated using spherical geometry to account for different latitudes. Geographical considerations. Spherical trigonometry takes into account the curvature of the Earth when calculating prayer times for different locations, latitude and longitude. Each geographical location has different solar angles due to its latitude and longitude. Spherical trigonometric calculations allow for precise adjustments based on these coordinates, ensuring accurate prayer times regardless of where one is located on Earth. Elevation above sea level. The altitude of a location can also affect solar observations. Spherical trigonometry can incorporate adjustments for elevation, enhancing accuracy in determining prayer times. Practical applications. The practical applications of spherical trigonometry in calculating prayer times include software development. Many applications utilize spherical trigonometric calculations to provide accurate prayer times based on users' geographical locations. These applications often employ algorithms that consider local conditions and astronomical data. Community practices. Accurate determination of prayer times fosters community cohesion by ensuring that congregational prayers occur at appropriate times, enhancing communal worship experiences. Conclusion. Spherical trigonometry is essential for accurately calculating Islamic prayer times by accounting for the Earth's curvature and solar positions relative to specific locations. Through precise mathematical modeling, it ensures that Muslims can observe their prayers at correct times throughout the day and year, reflecting a harmonious blend of faith and scientific understanding. If you have any further questions or need additional information on this topic or related subjects, please let me know. The sun's declination angle plays a crucial role in the application of spherical trigonometry for calculating prayer times in Islam. Here's how it influences these calculations. Understanding the declination angle. The declination angle, DD, is defined as the angle between the rays of the sun and the plane of the Earth's equator. It varies throughout the year due to the tilt of the Earth's axis, approximately 23.45 degrees, and its orbit around the sun. This angle affects how high the sun rises in the sky at different times of the year, which is essential for determining prayer times. Role in prayer time. Calculations Fajr and Isha timings. Fajr, dawn. The time for Fajr prayer begins when the sun is approximately 18 degrees below the horizon. The declination angle helps determine when this condition is met, as it influences how light spreads across the horizon at dawn. Isha, evening. Similarly, Isha prayer time starts when twilight has disappeared, typically defined as when the sun is about 17 degrees below the horizon. The declination angle again plays a role in determining this timing. Calculating solar angles. Spherical trigonometry uses the declination angle to calculate solar angles at specific times of day. This involves determining how far below or above the horizon the sun is at various points in time, which directly affects when prayers should be performed. Geographical variation. The declination angle varies with seasons, affecting different geographical locations differently. For example, during summer months, regions farther from the equator experience longer daylight hours and higher solar angles, which can alter prayer timings. Calculating accurate prayer times requires adjusting for both latitude, the geographical location, and declination angle, ensuring that all factors influencing solar position are considered. Mathematical formulations. The declination angle can be calculated using specific equations that take into account the day of the year, D. For example, sin sin 23:45, cos 360,365 D plus 10, sin 23:45, cos 365,360 D plus 10. This calculation allows for determining how high or low in the sky the sun will be at any given time throughout the year, which is essential for setting accurate prayer times. Integration with technology. Modern applications and software utilize spherical trigonometry and solar declination calculations to provide accurate prayer times based on user location. These tools often incorporate algorithms that adjust for local conditions and astronomical data. Conclusion. The sun's declination angle is a fundamental component of spherical trigonometry used to calculate Islamic prayer times accurately. By understanding how this angle varies throughout the year and affects solar positions, practitioners can ensure they observe their prayers at appropriate times. This interplay between mathematics and religious observance highlights the importance of precise calculations in daily life for millions of Muslims around the world. If you have any further questions or need additional information on this topic or related subjects, please let me know. The sun's declination angle and the equation of time are both critical components in accurately calculating Islamic prayer times. Here's how they interact and contribute to these calculations. Understanding the declination angle. The declination angle, DD, is the angle between the rays of the sun and the plane of the Earth's equator. It varies throughout the year due to the tilt of the Earth's axis and its elliptical orbit around the sun. This angle affects how high the sun appears in the sky at different times of the year, which is essential for determining when specific prayers should be performed. The equation of time. The equation of time, EOT, accounts for discrepancies between solar time, the time based on the position of the sun, and mean time, the average time kept by clocks. This discrepancy arises due to eccentricity of Earth's orbit. The Earth's orbit is not a perfect circle, leading to variations in solar time throughout the year. Axial tilt. The tilt of the Earth's axis causes changes in solar position relative to local time. The EOT is expressed as a function that varies throughout the year, typically oscillating with a sinusoidal pattern. It can cause differences in solar noon by several minutes over the course of a year. Interaction between declination angle and equation of time. When calculating prayer times, both the declination angle and the equation of time must be considered simultaneously. Dur time calculation. The Dur prayer occurs when the sun has passed its zenith, highest point. The local solar noon can be calculated using Tahur 2 plus DD plus ZL15 to 12 dim Z15L, where Tahur is the time for Dur. DDT is derived from the equation of time, correcting for discrepancies between mean time and solar time. ZZ is the local time zone, L is the longitude. Fajr and Isha calculations, the timings for Fajr and Isha depend on specific angles below the horizon, commonly 18 degrees for Fajr and 17 degrees for Isha. These angles are influenced by both declination and local solar conditions. The declination angle helps determine how low in the sky the sun must be for these prayers to commence. Practical application. In practice, prayer timing calculations involve daily adjustments. Both declination angles and EOT values change daily, necessitating adjustments to prayer times based on current calculations rather than fixed values. Geographical considerations. Latitude affects how declination angles impact solar positions, while EOT adjustments are universal across locations but require local context for accurate timing. Conclusion. The interaction between the sun's declination angle and the equation of time is essential for accurately calculating Islamic prayer times. By incorporating both elements into mathematical models, practitioners can ensure that prayers are observed at appropriate times throughout the year, reflecting a harmonious blend of faith and scientific understanding. This meticulous approach underscores how mathematics serves as a vital tool in religious observance, enhancing both accuracy and spiritual practice. If you have any further questions or need additional information on this topic or related subjects, please let me know. The importance of mathematics. Mathematics is often regarded as the language of the universe, a fundamental tool that underpins various aspects of human life and society. Its significance extends far beyond the confines of academia. It plays a crucial role in the development of civilization and shapes our understanding of the world. This section explores the multifaceted importance of mathematics, highlighting its contributions to society, technology, and individual cognitive development. Foundation for scientific advancement. Mathematics is at the core of scientific inquiry. It provides the tools necessary for formulating theories, conducting experiments, and analyzing data. The history of mathematics reveals that societies that prioritized mathematical knowledge made substantial progress in science and technology. For instance, physics, mathematical equations describe fundamental laws of nature, such as Newton's laws of motion and Einstein's theory of relativity. Biology, mathematical models help understand population dynamics, genetic variation, and disease spread, leading to advancements in public health. Engineering. Mathematics is essential for designing structures, analyzing materials, and optimizing systems in civil, mechanical, and electrical engineering. Role in economic development. Mathematics is integral to economic growth and development. It enables individuals and organizations to make informed decisions based on quantitative analysis. Key areas where mathematics impacts economics include financial analysis. Mathematical models assess investment risks, optimize portfolios, and evaluate market trends. Supply chain management. Operations research techniques optimize logistics, inventory management, and production processes. Statistical analysis. Econometrics uses statistical methods to analyze economic data, informing policy decisions and business strategies. Enhancing cognitive skills. The study of mathematics fosters critical thinking and analytical skills. Engaging with mathematical concepts develops reasoning abilities that are applicable in everyday life. Benefits include analytical thinking. Mathematics encourages logical reasoning and problem-solving skills essential for navigating complex situations. Creativity. Solving mathematical problems often requires innovative thinking and creative approaches. Quantitative literacy. A strong foundation in mathematics equips individuals with the skills needed to interpret data and make informed decisions in a data-driven world. Addressing global challenges. Mathematics plays a vital role in tackling some of the most pressing global issues we face today. Climate change. Mathematical models analyze climate data to understand patterns, predict future scenarios, and inform policy decisions aimed at mitigating climate impacts. Public health. Epidemiological models use mathematics to predict disease outbreaks and evaluate intervention strategies. Resource management. Mathematics helps optimize resource allocation in agriculture, energy production, and environmental conservation. Cultural significance. Mathematics is not only a scientific tool, but also an integral part of culture. It has influenced art, music, architecture, and philosophy throughout history. Art, the Golden Ratio and Fibonacci sequence have inspired artists like Leonardo da Vinci and Salvador Dali in their compositions. Music, mathematical patterns underpin musical scales, rhythms, and harmonies. Architecture, mathematical principles guide structural design and aesthetic proportions in buildings. Conclusion. The importance of mathematics cannot be overstated. It is a cornerstone of human knowledge that drives progress across multiple domains. From scientific advancements to economic development and cultural achievements, mathematics shapes our understanding of the world while equipping individuals with essential skills for personal and professional success. As we continue to face complex global challenges, Fostering mathematical literacy will be crucial for empowering future generations to innovate and thrive in an increasingly interconnected world. This section elaborates on the importance of mathematics by discussing its foundational role in various aspects of society. If you would like further elaboration on specific points or additional topics included within this discussion on the importance of mathematics, please let me know. Conclusion. In this exploration of advanced mathematical concepts and their applications, we have traversed a wide landscape of ideas that underscore the profound impact of mathematics on various fields and aspects of life. From the foundational principles of unique numbers to the complexities of network theory, each chapter has illuminated how mathematics serves as a vital tool for understanding and solving real-world problems. Key takeaways: interconnectedness of concepts. The diverse mathematical concepts discussed, ranging from graph theory and linear algebra to differential equations and game theory, are interconnected. Each area contributes to a broader understanding of systems, whether in nature, technology, or human behavior. Real-world applications. Mathematics is not merely an abstract discipline, it has practical applications across numerous domains, including science, engineering, finance, biology, and social sciences. The ability to model complex systems mathematically allows for informed decision-making and innovative solutions to contemporary challenges. Cognitive development. Engaging with advanced mathematics enhances critical thinking, analytical reasoning, and problem-solving skills. These cognitive abilities are essential not only for academic success, but also for navigating the complexities of everyday life. Addressing global challenges. Mathematics plays a crucial role in tackling pressing global issues such as climate change, public health crises, and economic instability. By providing tools for modeling and analysis, mathematics empowers individuals and organizations to make data-driven decisions that can lead to positive societal outcomes. Cultural significance. Beyond its practical applications, mathematics has cultural implications that enrich our understanding of art, music, architecture, and philosophy. Its influence permeates various facets of human creativity and expression. The path forward. As we move into an increasingly complex and data-driven world, the importance of mathematical literacy will only grow. Educators, policymakers, and society as a whole must prioritize mathematics education to equip future generations with the skills necessary to thrive in this environment. By fostering a culture that values mathematical thinking and problem-solving, we can empower individuals to contribute meaningfully to their communities and address the challenges that lie ahead. In conclusion, advanced mathematics is not just a subject confined to textbooks. It is a dynamic field that shapes our understanding of the universe and enhances our ability to innovate. Whether through scientific research, technological advancements, or informed policymaking, the principles of mathematics will continue to guide us toward a more informed and equitable future. This conclusion encapsulates the key themes discussed throughout the book, while emphasizing the significance of mathematics in various contexts. If you would like any modifications or additional points included in this conclusion, or if you need further assistance with any other aspect of your project, please let me know. The path forward. As we look to the future of mathematics education, it is clear that we stand at a pivotal moment characterized by rapid technological advancements and evolving pedagogical approaches. The integration of emerging technologies and innovative teaching methods has the potential to transform how mathematics is taught and learned, making it more accessible, engaging, and relevant for students of all backgrounds. Embracing emerging technologies, adaptive learning platforms. These platforms personalize the learning experience by adjusting the difficulty of problems based on individual student performance. This tailored approach ensures that students receive the support they need to master challenging concepts, fostering a growth mindset and enhancing their mathematical skills. Augmented reality, AR. By overlaying digital information onto real-world environments, Arkansas allows students to visualize complex mathematical concepts in an interactive manner. This hands-on approach can make abstract ideas more tangible, helping students grasp difficult topics more easily. AI-powered tutors. Artificial intelligence is revolutionizing math education by providing personalized tutoring experiences that adapt to each student's strengths and weaknesses. AI-driven platforms can offer customized lessons and practice problems, ensuring that students receive targeted support as they progress through their studies. Rethinking pedagogical approaches. The future of mathematics education also requires a shift in pedagogical practices. Traditional methods focused on rote memorization and procedural tasks must evolve to prioritize critical thinking, creativity, and problem-solving skills. Key strategies include active learning. Encouraging students to engage with non-routine problems fosters critical thinking and helps them develop a deeper understanding of mathematical concepts. Collaborative learning. Promoting teamwork and discourse among students enhances emotional intelligence while allowing them to tackle math challenges together. Inquiry-based learning. Encouraging students to explore mathematical concepts through investigation and discovery nurtures curiosity and fosters a love for learning. Preparing students for future challenges. As we equip students with the skills needed for success in an increasingly complex world, it is essential to focus on developing competencies that extend beyond traditional mathematics. These include critical thinking. Students must learn to analyze information, evaluate evidence, and make informed decisions based on quantitative data. Creativity. Encouraging innovative thinking will enable students to approach problems from multiple angles and devise unique solutions. Adaptability. In a rapidly changing world, students must be prepared to adapt their skills to new technologies and methodologies as they emerge. The role of educators and policymakers. To facilitate this transformation in mathematics education, collaboration among educators, parents, and policymakers is essential. Together, we can create an environment that supports innovative teaching practices while ensuring equitable access to resources for all students. This partnership will involve professional development, providing teachers with ongoing training in emerging technologies and pedagogical strategies will empower them to implement effective practices in their classrooms. Curriculum. Reform. Revising curricula to incorporate real-world applications of mathematics will enhance student engagement and demonstrate the relevance of math in everyday life. Community engagement. Involving parents and community members in the educational process fosters a supportive environment that values mathematics as a critical skill for future success. Conclusion. The path forward for mathematics education is one filled with promise and potential. By embracing emerging technologies, rethinking pedagogical approaches, and fostering collaboration among stakeholders, we can create a dynamic learning environment that equips students with the skills they need to thrive in an ever-changing world. As we move forward, let us remain committed to nurturing a love for mathematics while preparing future generations to tackle the challenges that lie ahead with confidence and creativity. This section outlines the vision for the future of mathematics education by emphasizing the importance of technology integration, innovative teaching methods, and collaborative efforts among educators and stakeholders. Or if you would like any changes or additional content included in this section, or if you need further assistance with any other aspect of your project, please let me know. Chapter 23, Mathematical Biology. Introduction to Mathematical Biology. Mathematical biology applies mathematical techniques to understand biological systems and phenomena. This interdisciplinary field combines mathematics with biology to model processes such as population dynamics, disease spread, genetic variation, and ecological interactions. Key concepts: population dynamics models. These models describe how populations change over time due to births, deaths, immigration, emigration, using differential equations or difference equations. For example, DND equals sign Rn, 1 NK, DDN, 8 Rn, 1 Kn, where Nn is population size at time Tt, R is growth rate, Kk is carrying capacity. Epidemiological models. Models such as SAR, susceptible, infected, recovered, help predict disease spread within populations based on contact rates between individuals. Mathematical biology, applications and insights. Introduction to mathematical biology. Mathematical biology is an interdisciplinary field that employs mathematical techniques and models to understand and analyze biological processes. This area of study has gained prominence as researchers increasingly recognize the importance of quantitative approaches in biology. By using mathematical frameworks, scientists can simulate complex biological systems, predict behaviors, and inform experimental designs. Key concepts in mathematical biology. Mathematical biology encompasses a variety of concepts and techniques, including ordinary differential equations, ODEs, ODs are commonly used to model dynamic systems in biology, such as population growth, disease spread, and cellular processes. For example, the CR model, susceptible, infected, recovered, is represented by the following equations. DSD, BSI, DDS, BSI, DID, BZ, GID, BSI, JU, DART, GID, DAR, GI, where SS represents susceptible individuals, 2 represents infected individuals, RR represents recovered individuals, BB is the transmission rate, and GG is the recovery rate. Statistical models. Statistical methods are employed to analyze biological data, identify trends, and make predictions. Techniques such as regression analysis and hypothesis testing are commonly used in fields like epidemiology and genetics. Network theory. This area focuses on the relationships between entities in biological systems, such as gene interactions or species interactions within ecosystems. Graph theory provides a framework for understanding these complex networks. Population dynamics. Mathematical models help describe how populations change over time due to factors like birth rates, death rates, immigration, and emigration. These models can inform conservation strategies and resource management. Applications of mathematical biology. Mathematical biology has broad applications across various fields. Conservation biology. Models assess species viability under changing environmental conditions, informing conservation strategies aimed at preserving biodiversity. For instance, mathematical models can predict how habitat loss affects population dynamics and guide efforts to protect endangered species. Drug development. Mathematical models predict how drugs interact with biological systems, guiding experimental designs during pharmaceutical research aimed at developing effective treatments against diseases. By simulating drug interactions at the cellular level, researchers can optimize dosage and delivery methods. Epidemiology. Mathematical models are essential for understanding how diseases spread through populations via contact networks. They inform public health interventions aimed at mitigating outbreaks effectively by predicting the impact of vaccination strategies or social distancing measures. Ecology. In ecological studies, mathematical modeling helps analyze food webs and predator-prey interactions. This understanding can inform ecosystem management practices and conservation efforts. Cellular biology. Mathematical models are used to study cellular processes such as cell division, signaling pathways, and metabolic networks. These models help researchers understand disease mechanisms and identify potential therapeutic targets. Conclusion. Mathematical biology provides essential insights into complex biological processes through quantitative modeling approaches. By integrating mathematical techniques with biological research, scientists can enhance their understanding of living systems while informing policies related to healthcare practices and broader ecological considerations regarding biodiversity conservation efforts. As the field continues to evolve, it holds great promise for addressing some of the most pressing challenges in biology and medicine today. This overview highlights the significance of mathematical biology along with its applications across various fields. If you have any further questions or need additional information on specific topics or aspects of this subject, please let me know. Recent applications of graph theory and machine learning. Graph theory and machine learning have increasingly become intertwined, leading to innovative applications across various fields. Here's a summary of how these concepts are being utilized in different domains. 1. Agricultural productivity crop rotation patterns. By analyzing relationships between different crops, graph theory can enhance agricultural productivity. Understanding the interactions between crops can inform better planting strategies, leading to improved yields and sustainable practices. 1. Machine learning graph-based algorithms. Machine learning leverages graph-based algorithms to improve predictive modeling accuracy. By representing data as graphs, these algorithms can capture complex relationships and interactions between entities, enhancing decision-making processes in various applications. 1. AI ethics bias. Detection. Graph theory aids in studying biases present in algorithms, ensuring fairness and equity throughout decision-making processes. By analyzing the relationships between data points, it becomes possible to identify and mitigate biases that could affect outcomes. 1. Human resources employee performance analysis. Graph theory can analyze relationships between job satisfaction and productivity, enhancing workplace environments. By mapping these connections, organizations can identify key factors that influence employee performance. 1. Financial technology, fintech, fraud. Detection. Network analysis improves fraud detection mechanisms by identifying unusual patterns and connections among transactions. This enhances security measures and helps prevent financial crimes. 1. Cognitive science, neural networks. Understanding the connections between neurons through graph theory enhances comprehension of brain functioning. This approach aids in studying cognitive processes and developing better models for neural activity. 1. Supply chain management logistics optimization. Graph theory is used to optimize logistics by analyzing relationships among suppliers and distributors. This leads to enhanced operational efficiencies, reducing costs and improving service delivery. 1. Risk management vulnerability assessment. Analyzing connections among assets helps assess vulnerabilities in systems, enhancing resilience against potential threats faced throughout operations. 1. Public policy, societal impact modeling. Graph theory can model societal impacts by assessing relationships between enacted policies, enhancing the effectiveness of decision-making processes. 1. Energy systems power grid analysis. Studying connections among energy sources using graph theory allows for optimizing distribution strategies, improving efficiency in energy management. 1. Urban planning city layout. Understanding, analyzing connections between infrastructure elements enhances livability through informed design decisions in urban planning. 1. Humanitarian aid relief network. Optimization. Graph theory is applied to analyze relief networks, optimizing resource allocation strategies during crises faced globally. 1. Historical analysis. Event connections. Studying historical events through graph analysis helps understand connections between individuals and groups, enriching comprehension regarding societal evolution over time. 1. Cultural studies, cultural exchange analysis. Understanding cultural exchanges through graph theory enriches appreciation for diversity experienced globally today by analyzing connections between societies. 1. Environmental studies, ecological impact assessment. Graph analysis assesses ecological impacts by studying connections among species, enhancing conservation efforts aimed at preserving biodiversity. Conclusion. The integration of graph theory with machine learning has opened new avenues for solving complex problems across various domains, from enhancing agricultural practices to improving fraud detection in finance. The applications are diverse and impactful. As technology continues to evolve, leveraging these mathematical concepts will be crucial for addressing contemporary challenges effectively. If you have any further questions or need additional information on specific applications or related topics, please let me know. Chapter 22, The Mathematics of Networks, continued. Applications of network theory, continued. Environmental studies. Assessing ecological impacts by studying connections among species and their habitats enhances comprehension regarding biodiversity and conservation efforts. Network models can illustrate food webs and predator-prey relationships, providing insights into ecosystem dynamics. Transportation networks analyzing transportation systems through network theory allows for optimization of routes and schedules, improving efficiency in public transit, freight logistics, and urban planning. By modeling roads, railways, and air traffic as networks, planners can identify bottlenecks and enhance connectivity. Telecommunication networks. Network theory is essential for designing and optimizing communication networks, including the internet and mobile networks. By analyzing the flow of information through nodes, servers, and edges, connections, engineers can improve data transmission efficiency and reliability. Epidemiology. In public health, network models help understand how diseases spread through populations by mapping interactions among individuals. This approach informs strategies for controlling outbreaks by identifying key individuals or groups that are central to transmission dynamics. Social media analysis. Social media platforms can be viewed as large-scale networks where users are nodes and interactions, likes, shares, comments, are edges. Analyzing these networks helps understand trends, influence, and information diffusion across platforms. Financial networks. In finance, network theory is used to analyze relationships between financial institutions, market participants, and assets. Understanding these connections helps assess systemic risk and develop strategies to mitigate financial crises. Supply chain networks. Modeling supply chains as networks allows businesses to optimize inventory management, distribution strategies, and supplier relationships. This approach enhances resilience against disruptions by identifying critical nodes in the supply chain. Cognitive networks. In cognitive science, network models represent the connections between neurons in the brain or concepts in human memory. Analyzing these networks provides insights into learning processes, memory retrieval, and cognitive function. Cultural networks. Cultural studies utilize network theory to analyze the relationships between cultural artifacts, for example, literature, art, and their creators or audiences. This approach helps understand cultural evolution and the spread of ideas across societies. Political networks. Political science employs network analysis to study relationships among political actors, for example, politicians, parties, and their interactions, for example, alliances, conflicts. This analysis aids in understanding power dynamics and electoral behavior. Ecosystem services networks. Understanding the interconnections between ecosystem services, for example, pollination, water purification, through network modeling, helps assess their collective impact on human well-being and environmental sustainability. Crime networks. Law enforcement agencies use network analysis to investigate criminal organizations by mapping relationships among offenders and their activities. This approach aids in dismantling organized crime syndicates. Conclusion: network theory provides a robust framework for analyzing complex systems characterized by interconnectedness across various domains. Its applications span social sciences, biology, economics, engineering, and beyond, making it an invaluable tool for understanding relationships within data and informing decision-making processes. Chapter 23. Conclusion summary of advanced mathematical concepts. Throughout this book, we have explored a wide range of advanced mathematical concepts and their applications across various fields. Unique numbers, their properties and significance in mathematics, basic foundations of numbers, concepts like concatenation, arithmetic sequences, and geometric sequences, Fibonacci numbers, their mathematical significance and appearance in nature, prime numbers, their role in number theory and cryptography, modular arithmetic, applications in computer science and cryptography, graph theory, analyzing relationships through vertices and edges, linear algebra, essential tools for solving systems of equations, statistics, methods for collecting and analyzing data, probability theory, quantifying uncertainty in various contexts, game theory, strategic interactions among rational decision-makers, differential equations, modeling change in dynamic systems, numerical methods, approximating solutions to complex problems, topology, studying properties that remain invariant under transformations, mathematical modeling, representing real-world systems with mathematical constructs, the role of mathematics in AI, foundations for machine learning algorithms, operations research, optimizing decision-making processes, fractal geometry, exploring self-similar patterns in nature, chaos theory, understanding complex systems with sensitive dependence on initial conditions, mathematical finance, analyzing financial markets using mathematical models, information theory, quantifying information storage and communication efficiency, mathematics in cybersecurity, protecting sensitive information through cryptographic techniques, mathematics in climate science, modeling climate systems to predict future changes, mathematical biology, understanding biological processes through quantitative modeling, the mathematics of networks, analyzing interconnected systems across various fields. The importance of mathematics. Mathematics is not merely a collection of abstract concepts. It is a powerful tool that shapes our understanding of the world around us. Its principles guide innovations across technology, science, finance, healthcare, environmental studies, social sciences, and more. As we face increasingly complex global challenges such as climate change, public health crises, economic instability, the need for mathematical thinking becomes ever more critical. By equipping ourselves with advanced mathematical knowledge and skills, we can better navigate these challenges and contribute to informed decision-making processes that benefit society as a whole. Final thoughts. In conclusion, this exploration of advanced mathematical concepts has highlighted their relevance across diverse domains while emphasizing the importance of fostering mathematical literacy in education and professional development settings alike. As we continue to advance into an era defined by data-driven decision-making processes fueled by technological innovation, understanding mathematics will remain paramount for future generations striving towards progress. This concludes our exploration of advanced mathematical concepts and their applications across various fields. If you would like to expand on any specific chapters further, or if you have additional topics you wish to include or discuss further details about any section presented here, please let me know. Introduction. Mathematics is a foundational discipline that provides tools for modeling, analyzing, and solving problems in diverse fields. This book aims to summarize advanced mathematical concepts and their practical applications, showcasing the relevance of mathematics in contemporary society. Unique numbers and their constraints. Definition of unique numbers. Unique numbers refer to numbers that possess distinct properties or characteristics, often serving as the basis for various mathematical theories. Significance of the number 1. The number 1 is crucial in various mathematical operations and serves as the identity element for multiplication. Basic foundations of numbers, concatenation of numbers. Concatenation involves joining numbers to form new values, leading to interesting properties when analyzing sequences. Arithmetic and geometric sequences. Arithmetic sequences have a constant difference between terms, while geometric sequences have a constant ratio, both essential in various mathematical applications. Fibonacci numbers. The Fibonacci sequence appears in nature and is defined by the recurrence relation Fn Fn1 plus Fn2 Fn Fn1 plus Fn2. The relationship between Fibonacci numbers and the golden ratio is also significant. Prime numbers definition and properties. Prime numbers are natural numbers greater than 1 that have no positive divisors other than 1 and themselves, playing a critical role in number theory. Applications in cryptography. Prime numbers are fundamental in cryptographic algorithms such as RSA, which relies on the difficulty of factorizing large primes. Modular arithmetic deals with integers under a modulus, widely used in computer science and cryptography to manage cyclic structures. Graph theory. Graph theory studies graphs composed of vertices connected by edges, with applications in social network analysis and routing algorithms. Linear algebra focuses on vectors, matrices, eigenvalues, and eigenvectors, essential for computer graphics and machine learning. Statistics involves collecting, analyzing, interpreting, presenting, and organizing data, with applications in healthcare, marketing, and social sciences. Probability theory. Probability theory studies random events and quantifies uncertainty through random variables and probability distributions. Game theory. Game theory analyzes strategic interactions among rational decision-makers, with applications in economics, political science, and biology. Differential equations. Differential equations describe relationships involving rates of change and are used extensively in physics, biology, and engineering. Numerical methods. Numerical methods provide techniques for approximating solutions to mathematical problems that cannot be solved analytically. Topology studies properties that remain invariant under continuous transformations, with applications in data analysis, topological data analysis, and robotics. Mathematical modeling involves creating abstract representations of real-world systems to simulate behaviors or predict outcomes. Applications in epidemiology models help predict disease spread, for example, SIR models, and inform public health strategies. Applications in environmental science mathematical models assess climate change impacts on ecosystems. The role of mathematics in artificial intelligence mathematics underpins AI development through linear algebra, calculus, probability, and statistics. Applications in deep learning. Deep learning utilizes complex neural networks for hierarchical data representation. Applications in natural language processing, NLP algorithms analyze text data using statistical methods to understand language patterns. Research employs mathematical techniques to optimize decision-making processes across industries. Applications in supply chain management or techniques streamline supply chains by optimizing inventory levels and transportation routes. Applications in transportation logistics models assist in designing efficient routing for delivery vehicles or public transportation systems. Fractal geometry. Fractal geometry studies complex structures exhibiting self-similarity across scales with applications in modeling natural phenomena and computer graphics. Applications in natural phenomena. Fractals model irregular shapes found in nature, for example, clouds. Applications in computer graphics. Fractal algorithms generate realistic textures and landscapes in CGI. Chaos theory. Chaos theory studies complex systems sensitive to initial conditions with applications in weather forecasting and economic modeling. Applications in weather forecasting. Chaos theory helps predict weather patterns due to atmospheric complexity. Applications in economic modeling. Economic models can exhibit chaotic behavior influencing market predictions. Mathematical finance. Mathematical finance applies mathematical methods to analyze financial markets with key concepts, including the Black-Scholes model for option pricing and portfolio theory for optimizing investment strategies. Applications. Option pricing, determining fair prices for options based on market conditions. Algorithmic trading, automating trading decisions based on statistical analysis. Information theory. Information theory quantifies information storage and communication efficiency, with key concepts like entropy and Shannon's theorem guiding applications such as data compression and error detection correction. Applications. Data compression. Techniques reduce data size for efficient storage. Error detection. Codes designed to detect errors during data transmission. Mathematics in cybersecurity. Mathematics ensures secure communication through cryptographic techniques, including public key cryptography, hash functions, and digital signatures that provide authentication for digital documents. Applications. Secure communications ensures confidentiality during transmission. Digital signatures provides authentication for digital documents. Mathematics in climate science. Mathematics models complex climate systems to predict future changes using differential equations governing climate dynamics while employing statistical downscaling techniques for localized predictions. Applications. Climate change. Projections. Simulating future scenarios based on emission pathways. Impact assessment. Evaluating potential impacts on ecosystems and human health. Mathematical biology. Mathematical biology applies mathematical techniques to understand biological systems through population dynamics models that describe how populations change over time, with applications including conservation biology and drug development. Applications. Conservation biology, assessing species viability. Drug development, predicting drug interactions with biological systems. The mathematics of networks. Network theory studies interconnected entities across various fields like sociology and biology, using concepts such as centrality measures to identify important vertices within a network. Chapter 1. Unique numbers and their constraints. Introduction to unique numbers. Unique numbers are defined by their distinct properties that set them apart from other numbers. These properties can manifest in various forms, such as mathematical uniqueness, application-specific characteristics, or their role in specific mathematical theories. Understanding unique numbers provides insight into the foundational elements of mathematics and their implications in real-world scenarios. The significance of the number one. The number one holds a special place in mathematics as the multiplicative identity. This means that any number multiplied by 1 remains unchanged. Its significance extends beyond arithmetic. Foundational role. The number 1 is the basis for counting and serves as the starting point for many mathematical concepts. Unit measurement. In various systems of measurement, 1 represents a single unit, forming the basis for more complex calculations. Identity element. In algebraic structures such as groups and rings, the number 1 serves as an identity element for multiplication. Applications of unique numbers. Unique numbers play a crucial role in various fields. Cryptography, prime numbers, which are unique in their indivisibility, are fundamental to encryption algorithms that secure digital communications. Computer science, unique identifiers, UIDs, such as those used in databases and programming, ensure that each entity can be distinctly recognized and accessed. Mathematical puzzles. Unique numbers often appear in recreational mathematics, where their properties can lead to intriguing challenges and solutions. Conclusion. The exploration of unique numbers reveals their foundational importance in mathematics and their diverse applications across multiple disciplines. Understanding these concepts not only enhances mathematical literacy but also fosters critical thinking skills essential for problem solving in real-world contexts. Chapter 2. Basic Foundations of Numbers. Concatenation of numbers. Concatenation is the process of linking together sequences of numbers to form new values. This operation is particularly useful in computer science and programming, where strings of digits may need to be combined for various applications. Examples of concatenation string manipulation. In programming languages, concatenating 123 inches and 456 inches results in 123,456 inches. Data representation. Concatenation is used to create unique identifiers or composite keys in databases. Arithmetic sequences. An arithmetic sequence is a sequence of numbers in which the difference between consecutive terms is constant. This property allows for straightforward calculations regarding the nth term or the sum of terms, formula for arithmetic sequences. The nth term of an arithmetic sequence can be expressed as an equal sign a1 plus n1 dan aa1 plus n1 d, where anan is the nth term, a1 is the first term, dd is the common difference. Geometric sequences. A geometric sequence is characterized by each term being multiplied by a constant factor to obtain the next term. This type of sequence has applications in finance, biology, and physics. Formula for geometric sequences. The nth term of a geometric sequence can be expressed as an a1r, n1, and xa1r, n1, where rr is the common ratio. Applications of sequences. Both arithmetic and geometric sequences have practical applications. Finance, arithmetic sequences can model linear growth, for example savings plans, while geometric sequences are used to model compound interest. Biology. Geometric sequences can describe population growth under ideal conditions. Conclusion. Understanding the basic foundations of numbers through concatenation, arithmetic sequences, and geometric sequences lays the groundwork for more complex mathematical concepts. These foundational elements are not only essential for academic pursuits, but also have significant applications in various fields. Chapter 3. Fibonacci numbers. Introduction to Fibonacci numbers. The Fibonacci sequence is one of the most famous numerical sequences in mathematics, defined by the recurrence relation Fn, f, n1 plus Fn2, Fn, f, n1 plus Fn2, with initial conditions f0 equals sign 0, f0 equals sign 0, and f1 equals sign 1, f1 equals sign 1. This sequence has captivated mathematicians and scientists alike due to its appearance in nature, art, and architecture. Properties of Fibonacci numbers. Fibonacci numbers exhibit several intriguing properties. Golden ratio. As the sequence progresses, the ratio between consecutive Fibonacci numbers approaches the golden ratio pH1. 6080387 pH1, 61803398887. Binet's formula. The nth Fibonacci number can be expressed using Binet's formula. Fnn 1 pH, n5 Fn into 5 pH and 1 pH in applications of Fibonacci numbers. Fibonacci numbers have diverse applications across various fields: nature, the arrangement of leaves on a stem, branching patterns in trees, and the arrangement of seeds in sunflowers often follow Fibonacci patterns. Art and architecture. The golden ratio derived from Fibonacci numbers influences aesthetics in art and design. Conclusion. The study of Fibonacci numbers reveals their mathematical beauty and significance across different domains. Their presence in nature and human creativity underscores the interconnectedness of mathematics with the world around us. Chapter 4. Prime numbers. Definition and properties. Prime numbers are natural numbers greater than 1 that have no positive divisors other than 1 and themselves. They are fundamental to number theory due to their role as building blocks for other integers. Key properties. Infinitude. There are infinitely many prime numbers. As proven by Euclid fundamental theorem of arithmetic, every integer greater than 1 can be uniquely factored into prime numbers. Applications in cryptography. Prime numbers play a crucial role in modern cryptography. RSA algorithm utilizes large prime numbers to create secure encryption keys. The security relies on the difficulty of factoring large composite numbers into their prime factors. Hash functions. Many cryptographic hash functions use prime numbers to ensure data integrity. Conclusion. Prime numbers are not only fascinating from a theoretical perspective, but also essential for practical applications in security and encryption. Their unique properties make them indispensable tools in various fields, especially computer science and cryptography. Chapter 5. Modular Arithmetic. Introduction to Modular Arithmetic. Modular arithmetic involves performing calculations with integers while considering only their remainders when divided by a fixed modulus. This system is widely used in computer science, cryptography, and number theory. Key concepts: congruence relation. Two integers AA and BB are said to be congruent modulo n if they leave the same remainder when divided by nn. Nabmodern applications. Modular arithmetic is crucial for algorithms that involve cyclic structures like clocks or circular buffers. Applications in cryptography. Modular arithmetic forms the backbone of many cryptographic algorithms. Public key cryptography. Algorithms like RSA rely on modular exponentiation for encryption and decryption processes. Hash functions. Many hashing algorithms utilize modular arithmetic to ensure uniform distribution of hash values. Conclusion. Understanding modular arithmetic provides essential insights into its applications across various fields, particularly computer science and cryptography. Its ability to simplify complex calculations makes it an invaluable tool for mathematicians and engineers alike. This structured format presents each chapter clearly while maintaining coherence throughout our discussions on advanced mathematical concepts. If you would like more chapters developed or specific topics expanded upon further, please let me know. Chapter 6. Graph Theory. Introduction to graph theory. Graph theory is a branch of mathematics that studies the relationships between objects represented as vertices or nodes and the connections between them as edges or links. This field has profound implications across various disciplines, including computer science, biology, social sciences, and logistics. Key concepts. Graph. A graph is defined as a pair G, del, VE, G is VE, where VV is a set of vertices and EE is a set of edges connecting pairs of vertices. Graphs can be directed or undirected, weighted or unweighted. Types of graphs. Directed graphs, digraphs. Edges have a direction indicating a one-way relationship. Undirected graphs, edges represent two-way relationships. Weighted graphs. Edges have associated weights or costs, often used to represent distances or capacities. Paths and cycles. A path is a sequence of edges connecting vertices without revisiting any vertex. A cycle is a path that starts and ends at the same vertex. Applications of graph theory. Graph theory has numerous applications in real-world scenarios. Social network analysis. Graphs model relationships among individuals in social networks, helping to analyze connectivity, influence, and community structures. Computer networks. The structure of computer networks can be represented as graphs, where rotors are vertices and connections are edges. Algorithms for routing data packets rely on graph theory. Transportation and logistics. Graphs are used to optimize routes for transportation systems, such as delivery services or public transit networks. Algorithms like Dijkstra's algorithm find the shortest paths between nodes. Conclusion. Graph theory provides powerful tools for analyzing complex systems characterized by interconnectedness. Its applications span various fields, making it an essential area of study for anyone interested in understanding relationships within data. Chapter 7. Linear Algebra. Introduction to Linear Algebra. Linear algebra is the branch of mathematics that deals with vector spaces and linear mappings between these spaces. It provides essential tools for solving systems of linear equations and has applications in various fields, including engineering, physics, computer science, and economics. Key concepts. Vectors. A vector is an ordered list of numbers that can represent points in space or quantities with direction. Vectors can be added together and multiplied by scalars. Matrices. A matrix is a rectangular array of numbers arranged in rows and columns. Matrices can represent linear transformations and systems of linear equations. Determinants and inverses. The determinant is a scalar value that provides information about the properties of a matrix, such as whether it is invertible. The inverse of a matrix AA is denoted A1A1 and satisfies the equation AA1 tron, where the skew is the identity matrix. Applications of linear algebra. Linear algebra has widespread applications across various domains. Computer graphics. Matrices are used to perform transformations such as rotation, scaling, and translation of images in computer graphics. Machine learning. Many machine learning algorithms rely on linear algebra for data representation and manipulation. For example, neural networks use matrices to represent weights and inputs. Economics. Input-output models in economics use matrices to analyze how different sectors of an economy interact with one another. Conclusion. Linear algebra serves as a fundamental pillar in mathematics with extensive applications across multiple disciplines. Its concepts are critical for understanding complex systems and solving practical problems in technology and science. Chapter 8. Statistics. Introduction to Statistics. Statistics is the science of collecting, analyzing, interpreting, presenting, and organizing data. It plays a crucial role in decision-making processes across various fields by providing methods to summarize information and draw conclusions from data sets. Key concepts: descriptive statistics. These statistics summarize data using measures such as mean, average, median, middle value, mode, most frequent value, variance, measure of spread, and standard deviation, average distance from the mean. Inferential statistics. This branch allows us to make predictions or generalizations about a population based on sample data. Techniques include hypothesis testing, confidence intervals, and regression analysis. Probability distributions. Probability distributions describe how probabilities are distributed over values. Common distributions include normal distribution, bell curve, binomial distribution for binary outcomes, and Poisson distribution for counting events. Applications of statistics. Statistics has diverse applications across many fields. Healthcare, used in clinical trials to assess the effectiveness of treatments and interventions. Marketing, analyzes consumer behavior through surveys and experiments to inform marketing strategies. Social sciences helps researchers analyze survey data to understand social trends and relationships among variables. Conclusion. Statistics provides essential tools for understanding data-driven decision-making processes. Its applications span numerous fields, making it an indispensable discipline in today's data-centric world. Chapter 9. Probability theory. Introduction to probability theory. Probability theory is the mathematical framework for quantifying uncertainty. It provides tools for modeling random events and making predictions based on incomplete information. Key concepts. Random variables. A random variable assigns numerical values to outcomes of random phenomena. It can be discrete, taking specific values, or continuous, taking any value within an interval. Probability distributions. These describe how probabilities are assigned to different outcomes. Common distributions include normal distribution, characterized by its bell-shaped curve. Many natural phenomena follow this distribution. Binomial distribution models the number of successes in a fixed number of independent Bernoulli trials. Expected value. The expected value, mean, of a random variable represents its long-term average value over many trials. It is calculated by summing all possible values weighted by their probabilities. Applications of probability theory. Probability theory finds applications in various domains. Finance, used to assess risk and make investment decisions based on uncertain future returns. Insurance, helps calculate premiums based on the likelihood of events occurring. Machine learning. Many algorithms rely on probabilistic models to make predictions based on uncertain data. Conclusion. Probability theory provides essential insights into uncertainty and randomness. Its principles are foundational for making informed decisions in various fields ranging from finance to artificial intelligence. Chapter 10. Game theory. Introduction to game theory. Game theory is the study of strategic interactions among rational decision makers. It provides a framework for analyzing situations where individuals or groups make decisions that affect one another's outcomes. Key concepts. Nash equilibrium. A situation where no player can benefit by changing their strategy while others keep theirs unchanged. It represents a stable state in strategic interactions. Cooperative versus non-cooperative games. Cooperative games involve binding agreements among players. Non-cooperative games focus on individual strategies without collaboration. Zero-sum games. Situations where one player's gain is exactly balanced by another player's loss, often used to model competitive scenarios. Applications of game theory. Game theory has diverse applications across various fields. Economics, analyzes market competition, bargaining scenarios and auction designs. Political science, models voting behavior, coalition formation and international relations. Biology, studies evolutionary strategies among species competing for resources or mates through evolutionary game theory. Conclusion game theory provides valuable insights into strategic decision-making processes across multiple disciplines. Its principles help understand competitive behaviors in economics, politics, biology, and beyond. This structured approach continues our exploration into advanced mathematical concepts by providing detailed chapters that cover key ideas along with their applications. If you would like me to continue developing more chapters, or if you have specific topics you want expanded upon further, please let me know. Chapter 11. Differential equations. Introduction to differential equations. Differential equations are mathematical equations that relate a function to its derivatives. They are fundamental in describing various phenomena in physics, engineering, biology, and economics. By modeling how quantities change with respect to one another, differential equations provide insights into dynamic systems. Key concepts: ordinary differential equations, ODEs. These involve functions of a single variable and their derivatives. An example of an ODE is di dxy so dx di plus u 0, which describes exponential decay. Partial differential equations, PDEs. These involve functions of multiple variables and their partial derivatives. An example is the heat equation ut eta T 2 added to 2 which models heat distribution over time. Initial and boundary conditions. Solutions to differential equations often require specific conditions at the start, initial conditions, or at the boundaries of the domain, boundary conditions, to ensure uniqueness. Applications of differential equations. Differential equations are widely used in various fields. Physics. They describe motion, wave propagation, heat conduction, and other physical phenomena. For example, Newton's second law can be expressed as a differential equation relating force, mass, and acceleration. Biology models population dynamics through logistic growth equations or predator-prey interactions, helping to understand species interactions and ecosystem behavior. Engineering, used in control systems to model dynamic behaviors of systems such as electrical circuits or mechanical systems. Conclusion: differential equations are essential tools for modeling change in various scientific disciplines. Their ability to describe complex relationships between variables makes them invaluable for understanding dynamic systems in nature and technology. Chapter 12. Numerical methods. Introduction to numerical methods. Numerical methods are techniques used for approximating solutions to mathematical problems that cannot be solved analytically. They are essential in scientific computing, engineering simulations, and data analysis. Key concepts: root-finding algorithms. Methods such as the Newton-Raphson method or bisection method are used to find roots of equations numerically. These algorithms iteratively converge to a solution. Numerical integration. Techniques like Simpson's rule or the trapezoidal rule approximate the integral of functions when analytical solutions are difficult to obtain. These methods provide estimates for areas under curves. Finite difference methods, used for solving differential equations by approximating derivatives with difference equations. This approach is common in numerical simulations of physical phenomena. Applications of numerical methods. Numerical methods have diverse applications across various domains. Engineering simulations, used in finite element analysis, FEA, for structural engineering to simulate physical phenomena like stress, strain, and thermal effects. Weather forecasting. Numerical weather prediction models rely on complex algorithms to simulate atmospheric conditions based on initial data inputs. Finance. Numerical methods help in option pricing models and risk assessment by simulating various scenarios based on market data. Conclusion. Numerical methods provide powerful tools for approximating solutions to complex mathematical problems. Their applications across science and engineering highlight their importance in practical problem solving. Chapter 13. Topology. Introduction to topology. Topology is the branch of mathematics that studies properties that remain invariant under continuous transformations. It focuses on the qualitative aspects of space rather than quantitative measurements. Topology has applications in various fields, including data analysis, robotics, and theoretical physics. Key concepts: open and closed sets. In topology, an open set is a collection of points where each point has a neighborhood entirely contained within the set. A closed set contains all its limit points. Homeomorphism. A continuous function between two topological spaces that has a continuous inverse. If two spaces are homeomorphic, they are considered topologically equivalent. Compactness. a property of a space that generalizes the notion of closed and bounded subsets in Euclidean space. Compact spaces have important implications in analysis and topology. Applications of topology. Topology has numerous applications across different fields. Data analysis, topological data analysis, TDA, is used to study the shape of data and extract meaningful insights from high-dimensional datasets. Robotics, topology helps in motion planning by understanding configuration spaces representing all possible positions of a robot. Conclusion. Topology provides essential tools for understanding the properties of space and continuity. Its applications across diverse fields demonstrate its significance in both theoretical mathematics and practical problem solving. Chapter 14. Mathematical Modeling. Introduction to mathematical modeling. Mathematical modeling involves creating abstract representations, models of real-world systems using mathematical language. Models can be used to simulate behaviors or predict outcomes based on given parameters and relationships between variables. Key concepts. Deterministic models, models where outcomes are precisely determined by parameters, for example, population growth models. Stochastic models, models that incorporate randomness and uncertainty, for example, stock market models. These models use probability distributions to account for variability in outcomes. Dynamic models, models that describe how systems evolve over time, often represented by differential equations or difference equations. Applications of mathematical modeling. Mathematical modeling has broad applications across various disciplines. Epidemiology, models such as SAR, susceptible, infected, recovered, help predict disease spread and inform public health strategies during outbreaks. Environmental science, models assess the impact of human activities on ecosystems, helping policymakers make informed decisions about conservation efforts. Economics, economic models help forecast market trends and analyze policy impacts using mathematical representations of economic relationships. Conclusion. Mathematical modeling serves as a powerful tool for understanding complex systems and predicting their behavior. Its applications across multiple fields underscore its importance in addressing real-world challenges. Chapter 15. The role of mathematics in artificial intelligence. Introduction to mathematics in AI. Mathematics plays a crucial role in artificial intelligence, AI, providing the foundational principles behind algorithms that enable machines to learn from data. Various mathematical disciplines contribute significantly to AI development, including linear algebra, calculus, probability theory, and statistics. Key concepts. Linear algebra, essential for understanding neural networks as they rely heavily on matrix operations for computations involving weights and inputs. Calculus, used in optimization problems to minimize loss functions during training processes in machine learning algorithms. Probability, theory, and statistics, fundamental for making predictions based on uncertain data and evaluating model performance through metrics like accuracy and precision. Applications of mathematics in AI. Mathematics underpins many AI technologies. Deep learning utilizes complex neural networks with multiple layers to learn hierarchical representations from large datasets. Natural language processing, NLP. Algorithms analyze text data using statistical methods to understand language patterns and generate human-like responses. Computer vision. Mathematical models help machines interpret visual information from images or video streams through techniques like convolutional neural networks, CNNs. Conclusion. The role of mathematics in artificial intelligence is foundational for developing effective algorithms capable of learning from data. Its principles guide innovations across various AI applications, transforming industries and enhancing our understanding of intelligent systems. This structured format continues our exploration into advanced mathematical concepts by providing detailed chapters that cover key ideas along with their applications. If you would like me to continue developing more chapters, or if you have specific topics you want expanded upon further, please let me know. Chapter 16. Operations Research. Introduction to Operations Research. Operations research, OR, is a discipline that uses advanced analytical methods to help make better decisions. It combines mathematical modeling, statistical analysis, and optimization techniques to solve complex problems in various fields, including logistics, finance, healthcare, and manufacturing. Key concept: linear programming, a method for optimizing a linear objective function subject to linear equality and inequality constraints. The simplex algorithm is commonly used to find the optimal solution. Integer programming, a type of linear programming where some or all variables are constrained to take integer values. This is particularly useful in scenarios such as scheduling and resource allocation. Simulation. Techniques like Monte Carlo simulation allow for modeling complex systems by generating random samples to estimate outcomes. This method is especially valuable when dealing with uncertainty. Applications of operations research. Operations research has a wide range of applications across different industries. Supply chain management or techniques help optimize logistics and inventory management, reducing costs and improving efficiency in supply chains. Transportation or models assist in designing optimal routing for delivery vehicles or public transportation systems, minimizing travel time and costs. Healthcare. In healthcare settings, Oregon can optimize patient scheduling, resource allocation, and treatment planning to enhance service delivery and patient outcomes. Conclusion. Operations research provides powerful tools for decision-making in complex environments. Its mathematical foundations enable organizations to optimize processes, improve efficiency, and achieve strategic goals across various sectors. Chapter 17. Fractal Geometry. Introduction to Fractal Geometry. Fractal geometry is the study of complex geometric shapes that exhibit self-similarity across different scales. Unlike traditional Euclidean geometry, which deals with simple shapes like lines and circles, fractal geometry explores intricate patterns found in nature and mathematics. Key concepts. Self-similarity, a property where a shape looks similar at different scales. For example, the branching patterns of trees or the structure of snowflakes exhibit self-similar characteristics. Fractal dimension, a measure that quantifies how a fractal scales differently than traditional geometric shapes. Fractals can have non-integer dimensions, indicating their complexity. Iterated function systems, IFS, a method for constructing fractals using a set of contraction mappings. The famous Sierpinski triangle is an example of a fractal generated by IFS. Applications of fractal geometry. Fractal geometry has diverse applications across various fields. Natural phenomena. Fractals are used to model irregular shapes in nature, such as coastlines, clouds, and mountain ranges. Computer graphics. Fractal algorithms generate realistic textures and landscapes in computer-generated imagery, CG, enhancing visual effects in films and video games. Signal processing. Fractal analysis is applied in signal processing to analyze complex signals and improve data compression techniques. Conclusion. Fractal geometry reveals the intricate patterns that underlie many natural phenomena. Its applications across science and art highlight the beauty and complexity of mathematical structures in the world around us. Chapter 18. Chaos Theory. Introduction to Chaos Theory. Chaos theory studies complex systems that exhibit sensitive dependence on initial conditions, commonly referred to as the butterfly effect. Despite being deterministic in nature, chaotic systems can display unpredictable behavior over time. Key concept: sensitivity to initial conditions. Small changes in initial conditions can lead to vastly different outcomes in chaotic systems. This concept is famously illustrated by the idea that a butterfly flapping its wings could influence weather patterns elsewhere. Strange attractors. Patterns that emerge in chaotic systems represent stable states toward which a system tends to evolve over time. These attractors can be highly complex and fractal-like in nature. Bifurcation theory studies how changes in parameters can cause sudden shifts in the behavior of a system, leading to different types of dynamics or stability. Applications of chaos theory. Chaos theory has applications across various fields. Weather forecasting. Understanding chaotic dynamics helps meteorologists predict weather patterns more accurately despite inherent uncertainties. Economics. Economic models can exhibit chaotic behavior, influencing market predictions and financial strategies based on unpredictable fluctuations. Biology. Chaos theory models population dynamics where small changes can lead to significant variations in species populations over time. Conclusion. Chaos theory provides valuable insights into the behavior of complex systems characterized by unpredictability. Its principles help us understand phenomena across various disciplines, from meteorology to economics. Chapter 19. Mathematical Finance. Introduction to Mathematical Finance. Mathematical finance applies mathematical methods to analyze financial markets and securities. It encompasses various models used for pricing derivatives, managing risk, and optimizing investment portfolios. Key concepts. Black-Scholes model. A mathematical model for pricing options that accounts for factors like volatility and time until expiration. It provides a theoretical estimate for the price of European-style options. Portfolio theory, developed by Harry Markowitz, this theory focuses on maximizing returns while minimizing risk through diversification. The efficient frontier represents optimal portfolios that offer the highest expected return for a given level of risk. Value at risk, VRR, a statistical measure that quantifies the potential loss in value of an asset or portfolio over a defined period for a given confidence interval. VIR is widely used in risk management practices. Applications of mathematical finance. Mathematical finance has significant applications in various domains. Risk management. Quantitative methods assess financial risks associated with investments or portfolios, helping firms develop strategies to mitigate potential losses. Algorithmic trading. Mathematical models guide automated trading strategies based on market signals and statistical analysis, allowing for rapid execution of trades based on predefined criteria. Conclusion. Mathematical finance provides essential tools for understanding financial markets and managing risks effectively. Its principles underpin many modern financial practices and innovations within the industry. Chapter 20. Information Theory. Introduction to Information Theory. Information theory is a branch of applied mathematics that deals with quantifying information storage and communication efficiency. Developed by Claude Shannon in the mid-20th century, it provides foundational concepts for understanding data transmission and processing. Key concepts: entropy, a measure of uncertainty or randomness in a set of data. In information theory, it quantifies the amount of information produced by a stochastic source. Higher entropy indicates more unpredictability. Mutual information measures the amount of information that one random variable contains about another random variable. It assesses dependencies between variables. Shannon's theorem establishes the maximum rate at which information can be transmitted over a communication channel without error, known as channel capacity. Applications of information theory. Information theory has diverse applications across multiple fields. Data compression. Techniques like Huffman coding reduce the size of data for efficient storage and transmission while preserving essential information. Error detection and correction. Codes are designed to detect and correct errors during data transmission, for example, Reed-Solomon codes, ensuring reliable communication over noisy channels. Conclusion. Information theory provides essential insights into data communication and processing. Its principles are foundational for modern telecommunications, computer science, and data science applications. Chapter 21. Mathematics in Cybersecurity. Introduction to Cybersecurity Mathematics. Mathematics plays a critical role in ensuring secure communication through cryptographic techniques. Various mathematical principles underpin modern cryptographic algorithms that protect sensitive information from unauthorized access. Key concepts. Public key cryptography utilizes asymmetric encryption methods where two keys, public and private, are used for secure communication, for example, RSA algorithm. The security relies on the difficulty of factoring large composite numbers into their prime factors. Hash functions produce unique fixed-size outputs from variable-size inputs. Hash functions ensure data integrity by detecting changes. e.g. SHA-256. Digital signatures provide authentication and integrity for digital documents or transactions using cryptographic techniques that verify the identity of the sender while ensuring that messages have not been altered during transmission. Applications of mathematics in cybersecurity. Mathematics is fundamental to various aspects of cybersecurity. Secure communications ensures that messages remain confidential during transmission over insecure channels, for example, HTTPS. Intrusion detection systems use statistical analysis and machine learning algorithms to identify unusual patterns that may indicate security breaches or cyber attacks. Conclusion. Mathematics serves as the backbone of cybersecurity practices by providing tools for encryption, authentication, and data integrity verification. Its principles are essential for protecting sensitive information in an increasingly digital world. Chapter 22. Mathematics in Climate Science. Introduction to Climate Science Mathematics. Mathematics plays a crucial role in climate science by providing tools for modeling complex climate systems and predicting future climate changes. Mathematical models help scientists understand interactions within the Earth's atmosphere, oceans, land surfaces, and biosphere. Key concepts: differential equations, used extensively to model physical processes governing climate dynamics such as heat transfer, fluid motion, and atmospheric circulation. Coupled models integrate various components, atmosphere, oceans, land surface, into a single framework for comprehensive climate simulations that account for feedback mechanisms among different parts of the Earth system. Statistical downscaling. Techniques refine coarse climate model outputs to provide localized predictions relevant for impact assessments on specific regions or communities affected by climate change. Applications of mathematics in climate science. Mathematical modeling has significant applications within climate science. Climate change projections. Mathematical models simulate future climate scenarios based on different greenhouse gas emission pathways, informing policymakers about potential impacts. Assessment. Models evaluate potential impacts of climate change on ecosystems, agriculture, water resources, human health, and infrastructure planning, helping communities adapt effectively to changing conditions. Conclusion. Mathematics is essential for understanding climate systems and predicting future changes due to anthropogenic influences. Its role in climate science underscores its importance as we confront global challenges related to environmental sustainability, while applying community detection algorithms to reveal clusters within networks. Applications: social network analysis, studying relationships among individuals or groups, biological networks, modeling interactions among proteins or genes. Conclusion. This book has explored a wide range of advanced mathematical concepts along with their applications across various fields such as engineering, economics, healthcare, technology, environmental science, social sciences, finance, security, and more. Mathematics continues to be an essential tool for understanding complex systems and solving practical problems faced by society today. This format presents our discussions clearly as a book while maintaining coherence throughout the topics covered. If you would like any changes or additional sections added, or if you need further assistance with any specific topic or formatting style, for example APA or MLA, please let me know. Advanced mathematical concepts and their applications, why advanced mathematics matters. Mathematics is often perceived as a challenging subject, but its significance extends far beyond the classroom. The study of advanced mathematical concepts equips individuals with critical thinking skills, enhances problem-solving abilities, and fosters logical reasoning. This paper explores the importance of advanced mathematics in various fields, emphasizing its relevance in education, professional development, and real-world applications. Cognitive development through advanced mathematics. Engaging with advanced mathematics encourages students to develop cognitive acuity and analytical skills. By tackling complex problems, students learn to dissect intricate issues into manageable components and devise coherent strategies to resolve them. This process cultivates abstract thinking and logical reasoning, which are essential for success in diverse disciplines. Key benefits: enhanced problem-solving skills. Students learn systematic approaches to tackle challenges. Improved logical reasoning. Higher mathematics fosters the ability to construct logical arguments and assess the validity of statements. Quantitative literacy. Mastery of numerical concepts enables informed decision-making based on data analysis. Applications of advanced mathematics in various disciplines. Advanced mathematics is not confined to theoretical pursuits. It has practical applications across numerous fields. Engineering mathematics is fundamental in engineering for establishing and solving mathematical models related to various engineering problems. For instance, calculus and differential equations are used to analyze systems' behavior under different conditions. Economics mathematical models are employed in macroeconomics to study exchange rates and fiscal policies. In microeconomics, optimization techniques help maximize consumer utility based on budget constraints. Computer science algorithms, data structures, and complexity theory are grounded in mathematical principles. Advanced mathematics enhances computational efficiency and problem-solving capabilities in software development. Environmental science mathematical modeling is crucial for understanding ecological systems and predicting environmental changes. Models help assess the impact of human activities on ecosystems and inform conservation strategies. Interdisciplinary integration of mathematics. The increasing integration of knowledge across disciplines highlights the necessity of advanced mathematics in various fields. The ability to model complex systems using mathematical techniques fosters collaboration between mathematicians and professionals from other domains. Case studies, biological modeling. Mathematical models help understand population dynamics and disease spread. Financial modeling. Quantitative methods assess risks and forecast market trends. Challenges in learning advanced mathematics. Despite its importance, many students struggle with advanced mathematical concepts due to the abstract nature of the subject. Common difficulties include lack of understanding of mathematical definitions and notation, difficulty in writing proofs or reasoning about concepts logically, misconceptions about the properties of mathematical concepts, strategies for enhancing mathematical understanding. To overcome these challenges, educators can implement strategies that promote a deeper understanding of advanced mathematics, encouraging active learning, engaging students through problem-solving activities enhances comprehension, utilizing technology. Software tools can aid in visualizing complex mathematical concepts, fostering collaborative learning. Group work allows students to share perspectives and approaches to problem-solving. Conclusion. The exploration of advanced mathematical concepts reveals their profound impact on cognitive development, professional opportunities, and real-world applications. Mastery of these concepts equips individuals with essential skills that transcend disciplinary boundaries, fostering analytical thinking, logical reasoning, and effective problem-solving capabilities. Embracing advanced mathematics is not merely an academic pursuit, it is a vital investment in personal growth and future success across various fields. This format presents the information as a cohesive paper or chapter within a book while maintaining clarity on the significance of advanced mathematics and its applications across multiple disciplines. If you would like any modifications or additional sections added, or if you need further assistance with specific formatting styles or topics, please let me know. Advanced mathematical concepts and their applications. Abstract. This chapter explores a wide range of advanced mathematical concepts and their applications across various fields, including economics, biology, computer science, and environmental science. Each section highlights key concepts, definitions, and real-world applications, demonstrating the integral role mathematics plays in understanding and solving complex problems. Introduction. Mathematics is a foundational discipline that provides tools for modeling, analyzing, and solving problems in diverse fields. This chapter aims to summarize advanced mathematical concepts and their practical applications, showcasing the relevance of mathematics in contemporary society. Unique numbers and their constraints. Definition of unique numbers. Unique numbers refer to numbers that possess distinct properties or characteristics. For example, the number 1 is often considered a foundational element in mathematics, serving as the basis for counting and arithmetic. Significance of the number 1. The number 1 is crucial in various mathematical operations and serves as the identity element for multiplication. Basic foundations of numbers. Concatenation of numbers. Concatenation involves joining numbers to form new values. This process can lead to interesting properties when analyzing sequences. Arithmetic and geometric sequences. Arithmetic sequences have a constant difference between terms, while geometric sequences have a constant ratio. Both are essential in various mathematical applications. Fibonacci numbers. The Fibonacci sequence appears in nature and is defined by the recurrence relation Fn(f)(n)(1) plus Fn(2). The relationship between Fibonacci numbers and the golden ratio is also significant. Prime numbers definition and properties. Prime numbers are natural numbers greater than 1 that have no positive divisors other than 1 and themselves. They play a critical role in number theory. Applications in cryptography. Prime numbers are fundamental in cryptographic algorithms such as RSA, which relies on the difficulty of factorizing large primes. Modular arithmetic. Modular arithmetic deals with integers under a modulus. It is widely used in computer science and cryptography to manage cyclic structures. Graph theory studies graphs composed of vertices connected by edges. It has applications in social network analysis and routing algorithms. Linear algebra. Linear algebra focuses on vectors, matrices, eigenvalues, and eigenvectors. It is essential for computer graphics and machine learning. Statistics. Statistics involves collecting, analyzing, interpreting, presenting, and organizing data. It has applications in healthcare, marketing, and social sciences. Probability theory. Probability theory studies random events and quantifies uncertainty through random variables and probability distributions. Game theory analyzes strategic interactions among rational decision makers. It has applications in economics, political science, and biology. Differential equations describe relationships involving rates of change. They are used extensively in physics, biology, and engineering. Numerical methods. Numerical methods provide techniques for approximating solutions to mathematical problems that cannot be solved analytically. Topology. Topology studies properties that remain invariant under continuous transformations. It has applications in data analysis, topological data analysis, and robotics. Mathematical modeling. Mathematical modeling involves creating abstract representations of real-world systems to simulate behaviors or predict outcomes. Applications in epidemiology models help predict disease spread, for example, SIR models, and inform public health strategies. Applications in environmental science mathematical models assess climate change impacts on ecosystems. The role of mathematics in artificial intelligence. Mathematics underpins AI development through linear algebra, calculus, probability, and statistics. Operations research employs mathematical techniques to optimize decision-making processes across industries. Applications in supply chain management or techniques streamline supply chains by optimizing inventory levels and transportation routes. Applications in transportation logistics models assist in designing efficient routing for delivery vehicles or public transportation systems. Fractal geometry. Fractal geometry studies complex structures exhibiting self-similarity across scales. Applications in natural phenomena. Fractals model irregular shapes found in nature, for example, clouds. Applications in computer graphics. Fractal algorithms generate realistic textures and landscapes in CGI. Chaos theory studies complex systems sensitive to initial conditions. Applications in weather forecasting. Chaos theory helps predict weather patterns due to atmospheric complexity. Applications in economic modeling. Economic models can exhibit chaotic behavior influencing market predictions. Mathematical finance applies mathematical methods to analyze financial markets. Key concepts. Black-Scholes model, a model for pricing options. Portfolio theory, maximizing returns while minimizing risk through diversification. Applications. Option pricing, determining fair prices for options based on market conditions. Algorithmic trading, automating trading decisions based on statistical analysis. Information theory quantifies information storage and communication efficiency. Key concepts. Entropy measures uncertainty or randomness. Shannon's theorem establishes maximum information transmission rates over channels. Applications. Data compression techniques reduce data size for efficient storage. Error detection, codes designed to detect errors during data transmission. Mathematics and cybersecurity. Mathematics ensures secure communication through cryptographic techniques. Key concepts. Public key cryptography, asymmetric encryption methods, hash functions, ensuring data integrity. Applications. Secure communications, confidentiality during transmission. Digital signatures, authentication for digital documents. Mathematics in climate science. Mathematics models complex climate systems to predict future changes. Key concepts. Differential equations governing climate dynamics. Statistical downscaling, refining climate model outputs for localized predictions. Applications. Climate change. Projections, simulating future scenarios based on emission pathways. Impact assessment, evaluating potential impacts on ecosystems and human health. Mathematical biology. Mathematical biology applies mathematical techniques to understand biological systems. Key concepts. Population dynamics models describe how populations change over time. Applications. Conservation biology, assessing species viability, drug development, predicting drug interactions with biological systems. The mathematics of networks. Network theory studies interconnected entities across various fields like sociology and biology. Key concepts. Centrality measures, identifying important vertices within a network. Applications. Social network analysis, studying relationships among individuals or groups. Biological networks, modeling interactions among proteins or genes. Conclusion. This chapter has explored a wide range of advanced mathematical concepts along with their applications across various fields such as engineering, economics, healthcare, technology, environmental science, social sciences, finance, security, and more. Mathematics continues to be an essential tool for understanding complex systems and solving practical problems faced by society today. This structured format presents our discussions clearly while maintaining coherence throughout the topics covered. Mathematics is often seen as an abstract and intimidating subject, confined to textbooks and classrooms. Many people view it as a series of complex equations and theories that are difficult to understand and apply in real life. However, in reality, mathematics is the hidden language of the universe, underpinning the very fabric of our existence. It is the code that governs the natural world, from the smallest particles to the vast expanses of the cosmos, from the intricate dance of celestial bodies to the complex workings of the human brain. Mathematical principles govern the world around us in ways we may not always realize. These principles help us understand the patterns and structures that make up our reality. This essay will embark on a captivating journey through the realm of advanced mathematics, demystifying complex concepts and revealing their practical applications in various fields. We will see how these abstract ideas translate into real-world solutions and innovations. We'll delve into the fascinating world of prime numbers, exploring their unique properties and their significance in cryptography and computer science. We will also explore the elegance of the Fibonacci sequence, a series of numbers that appears in various forms in nature, art, and architecture, and unravel the power of graph theory, which helps us understand networks and relationships in fields ranging from social media to biology. Through engaging examples and relatable scenarios, we will discover how linear algebra forms the backbone of machine learning, enabling computers to recognize patterns and make predictions, while statistics and probability help us make sense of uncertainty in our daily lives. Guiding decisions in everything from weather forecasting to financial planning, we will explore the strategic thinking behind game theory, which models competitive situations and helps us understand decision-making in economics, politics, and beyond, and witness how differential equations model change and motion in fields as diverse as physics and finance, providing insights into dynamic systems and processes. Join us as we unlock the power of advanced mathematics, revealing its hidden beauty and its profound impact on our modern world. We will see how mathematical thinking drives innovation and progress in countless areas of human endeavor. Prepare to see the world through mathematical lenses, gaining a newfound appreciation for this elegant and essential discipline. Mathematics is not just a subject, it is a way of understanding and interacting with the world around us. Prime numbers, those elusive integers, divisible only by one and themselves, have captivated mathematicians for centuries. Their unique properties and seemingly random distribution have sparked countless theorems and conjectures. But beyond their theoretical allure, prime numbers play a crucial role in our digital age, safeguarding our online transactions and communications. At the heart of modern cryptography lies the concept of public key encryption, a system that relies heavily on the properties of prime numbers. When you make an online purchase or send a secure message, prime numbers are working behind the scenes to protect your sensitive information. The security of public key encryption stems from the difficulty of factoring large numbers into their prime factors. While multiplying two prime numbers is a straightforward task, finding those prime factors given only their product is computationally expensive, especially for very large numbers. This asymmetry forms the foundation of secure communication channels, ensuring that only authorized parties with the necessary keys can decrypt and access the information. As we rely increasingly on digital platforms, the importance of prime numbers in safeguarding our privacy and security continues to grow. The Fibonacci sequence, a simple yet profound mathematical pattern, is found throughout the natural world, from the arrangement of petals in a flower, where each petal is positioned at a precise angle to the next, creating a beautiful and efficient spiral, to the spiral patterns of a nautilus shell, which grows in a logarithmic spiral, perfectly embodying the Fibonacci sequence in its structure. This sequence, where each number is the sum of the two preceding ones, for example 1, 1, 2, 3, 5, 8, exhibits a remarkable ability to describe growth and patterns in nature. It is a universal code that can be seen in the way plants grow, ensuring optimal space and resource usage. In the realm of botany, the Fibonacci sequence manifests in the arrangement of leaves on a stem, known as phyllotaxis. This pattern allows plants to maximize light capture and minimize shadow, enhancing their ability to photosynthesize efficiently. This arrangement ensures that each leaf receives maximum sunlight exposure by preventing leaves from directly overlapping. It is a brilliant natural strategy for survival and growth. The spiral patterns observed in sunflower heads and pine cones also follow the Fibonacci sequence, optimizing seed packing and maximizing reproductive efficiency. Each seed is placed at a precise angle, ensuring the most efficient use of space. Beyond the plant kingdom, the Fibonacci spiral appears in the arrangement of scales on a pineapple, where the pattern helps in the even distribution of nutrients and growth. The branching patterns of trees, which follow a predictable and efficient growth pattern, allowing for optimal sunlight exposure and nutrient distribution. And even the shape of a hurricane, where the powerful forces of nature align with this mathematical sequence, creating a mesmerizing and destructive spiral. These recurring patterns suggest a fundamental mathematical principle underlying the growth and development of natural systems. It is as if nature itself is following a blueprint, a code that ensures efficiency and beauty. The ubiquity of the Fibonacci sequence in nature highlights the interconnectedness of mathematics and the natural world, revealing the elegance and efficiency inherent in natural design. This elegant code is a testament to the intricate and wondrous ways in which life evolves and thrives. Section 4, Graph Theory, Mapping Connections in a Complex World. In an increasingly interconnected world, understanding relationships and networks is paramount. Graph theory, a branch of mathematics that studies graphs, provides a powerful tool for analyzing and visualizing connections between objects. From social networks to transportation systems, graph theory finds applications in diverse fields, helping us navigate the complexities of our interconnected world. A graph, in the context of graph theory, consists of vertices or nodes and edges or links that connect them. This simple representation allows us to model a wide range of real-world phenomena. For instance, in a social network, individuals can be represented as vertices and their friendships or connections as edges. Graph theory algorithms can then be used to analyze these networks, identifying influential individuals, detecting communities, and predicting information flow. In transportation, graph theory optimizes routes, minimizes travel time, and enhances the efficiency of logistics and delivery networks. From mapping the spread of diseases to understanding the structure of the internet, graph theory plays a crucial role in unraveling the complexities of our interconnected world, providing valuable insights into the relationships that shape our lives. Section 5, Linear Algebra, the Foundation of Machine Learning. Machine learning, a rapidly evolving field transforming industries from healthcare to finance, relies heavily on the principles of linear algebra. At its core, machine learning involves training algorithms to learn from data, making predictions, and improving their performance over time. Linear algebra provides the mathematical framework for representing data, performing operations on that data, and building the algorithms that power machine learning models. Vectors and matrices, fundamental concepts in linear algebra, are used to represent data points and the relationships between them. Matrix operations, such as multiplication and inversion, enable efficient data manipulation and transformation, essential for training complex machine learning models. Techniques like principal component analysis, or PCA, a dimensionality reduction technique, rely heavily on linear algebra to extract meaningful features from high-dimensional data. From image recognition to natural language processing, linear algebra forms the bedrock of machine learning, enabling algorithms to learn from data, make accurate predictions, and drive innovation across various industries. Further exploration of mathematical concepts and their applications. Let's continue our exploration by diving into additional advanced mathematical concepts, their implications, and how they connect to various fields such as physics, computer science, and economics. We'll also look at some mathematical tools and techniques that are widely used in research and industry. Mathematical analysis. Mathematical analysis is a branch of mathematics that deals with limits, continuity, differentiation, integration, and infinite series. Key concepts. Limits. The value that a function approaches as the input approaches a certain point. Limits are foundational for defining continuity and derivatives. Continuity. A function is continuous if small changes in the input result in small changes in the output. This concept is crucial for calculus. Differentiation. The process of finding the derivative of a function which measures how a function changes as its input changes. Derivatives have applications in physics, for example, velocity and acceleration. Integration. The process of finding the integral of a function, which can represent areas under curves or accumulated quantities. Applications of mathematical analysis, physics, used to model motion, waves, heat transfer, and other physical phenomena. Economics helps in modeling and optimizing functions related to cost, revenue, and profit. Linear algebra. Linear algebra is the branch of mathematics concerning linear equations, linear functions, and their representations through matrices and vector spaces. Key concepts: vectors, objects that have both magnitude and direction. They can represent points in space or quantities like velocity. Matrices, rectangular arrays of numbers that represent linear transformations. Matrices can be added, multiplied, and inverted. Eigenvalues and eigenvectors, important concepts that provide insights into the properties of linear transformations. They are used in various applications such as stability analysis and principal component analysis, PCA. Applications of linear algebra. Computer graphics. Linear algebra is fundamental for transformations such as rotation, scaling, and translation of images. Machine learning. Many algorithms rely on linear algebra concepts for data representation and manipulation. Probability theory. Probability theory is the mathematical study of random phenomena. It provides a framework for quantifying uncertainty. Key concepts: random variables. Variables whose values depend on the outcomes of random events. They can be discrete, for example, rolling a die, or continuous, for example, measuring temperature. Probability distributions. Functions that describe the likelihood of different outcomes. Common distributions include normal distribution, bell-shaped curve, characterized by its mean and standard deviation. Binomial distribution models the number of successes in a fixed number of independent Bernoulli trials. Expectation and variance. Expectation provides the average outcome of a random variable, while variance measures the spread or variability around that average. Applications of probability theory. Statistics forms the basis for statistical inference, hypothesis testing, and confidence intervals. Finance, used in risk assessment, option pricing models, for example, Black-Scholes, and portfolio management. Game theory. Game theory studies strategic interactions among rational decision makers. It provides tools for analyzing situations where individuals or groups make decisions that affect each other's outcomes. Key concepts. Nash equilibrium, a situation where no player can benefit by changing their strategy while others keep theirs unchanged. It represents a stable state in strategic interactions. Zero-sum games, situations where one player's gain is exactly balanced by another player's loss. These games are often used to model competitive scenarios. Applications of game theory. Economics analyzes market competition, bargaining scenarios, and auction designs. Political science models voting behavior, coalition formation, and international relations. Mathematical tools and technique. Several mathematical tools are essential for solving complex problems across various fields. Numerical methods. Numerical methods provide techniques for approximating solutions to mathematical problems that cannot be solved analytically. Common methods include Newton-Raphson method, used for finding successively better approximations to the roots or zeros of a real-valued function. Finite element method, FEM, a numerical technique for finding approximate solutions to boundary value problems for partial differential equations. Statistical software. Statistical software packages like R, Python, with libraries such as NumPy and SciPy, SAS, and MATLAB, are widely used for data analysis, modeling, and simulation. Conclusion. The exploration of mathematical analysis, linear algebra, probability theory, game theory, and various mathematical tools highlights the diverse applications of mathematics across disciplines. These concepts not only enhance our understanding, but also provide powerful frameworks for solving real-world problems. If there are specific topics you'd like to explore further, such as applications in artificial intelligence or deeper dives into any particular mathematical theory, please let me know, continuing the exploration of advanced mathematical concepts and their applications. Let's delve deeper into additional advanced mathematical topics, exploring their implications, applications, and connections to various fields. We'll cover areas such as complex analysis, statistics, optimization, and their relevance in real-world scenarios. Complex analysis. Complex analysis is the study of functions that operate on complex numbers. It has profound implications in various fields of mathematics and applied sciences. Key concepts. Complex numbers. Numbers of the form z equals sine a plus bis equals sine a plus bi, where a and bb are real numbers, and i2 is the imaginary unit, with i.e. 2 os 1 i is 2 to 8 1. Analytic functions, functions that are differentiable at every point in their domain. They satisfy the Cauchy-Riemann equations, which ensure they are smooth and well-behaved. Contour integration, a method of integrating functions along a path or contour in the complex plane. It is used to evaluate integrals that are difficult to compute using real analysis. Applications of complex analysis, fluid dynamics. Used to model potential flow and analyze fluid motion. Electrical engineering. Complex analysis is integral in analyzing AC circuits, where voltages and currents can be represented as complex numbers. Statistics and data analysis. Statistics is the science of collecting, analyzing, interpreting, presenting, and organizing data. It provides tools for making informed decisions based on data. Key concepts: descriptive statistics, methods for summarizing and describing the essential features of data sets, for example, mean, median, mode, variance. Inferential statistics, techniques that allow us to make generalizations or predictions about a population based on sample data. This includes hypothesis testing and confidence intervals. Regression analysis, a statistical method for modeling the relationship between a dependent variable and one or more independent variables. Linear regression is one of the simplest forms. Applications of statistics healthcare, used in clinical trials to determine the effectiveness of new treatments. Marketing helps analyze consumer behavior and preferences through surveys and A/B testing. Optimization. Optimization involves finding the best solution from a set of feasible solutions. It is widely used in various fields to maximize or minimize objectives subject to constraints. Key concepts. Objective function, the function that needs to be maximized or minimized. Constraints, conditions that must be satisfied for a solution to be feasible. Linear programming, a method for optimizing a linear objective function, subject to linear equality and inequality constraints. The simplex algorithm is commonly used for solving linear programming problems. Applications of optimization operations research, used in logistics for optimizing supply chain management and resource allocation. Finance, portfolio optimization seeks to maximize returns while minimizing risk based on historical data. Mathematical modeling involves creating abstract representations, models, of real-world systems using mathematical language. Models can be used to simulate behaviors or predict outcomes. Types of mathematical models. Deterministic models, models where outcomes are precisely determined by parameters, for example, population growth models. Stochastic models, models that incorporate randomness and uncertainty, for example, stock market models. Applications of mathematical modeling, environmental science, used to model climate change impacts and predict ecological outcomes. Economics. Economic models help forecast market trends and analyze policy impacts. Discrete mathematics. Discrete mathematics deals with structures that are fundamentally discrete rather than continuous. It includes topics such as graph theory, combinatorics, and number theory. Key concepts: graph theory, the study of graphs as mathematical structures used to model pairwise relationships between objects. Combinatorics, the branch of mathematics dealing with counting, arrangement, and combination of objects. Applications of discrete mathematics, computer science. Algorithms often rely on graph theory for network design and optimization problems. Cryptography. Many cryptographic protocols use concepts from number theory and combinatorics to secure information. Conclusion: the exploration of complex analysis, statistics, optimization, mathematical modeling, and discrete mathematics reveals the depth and breadth of mathematics as a discipline. Each topic not only enhances our understanding, but also provides powerful tools for solving practical problems across various fields such as engineering, economics, healthcare, and computer science. If there are specific areas you would like to explore further, such as applications in artificial intelligence or deeper dives into particular mathematical theories, please let me know. Continuing the exploration of advanced mathematical concepts and their applications. Let's further explore additional advanced mathematical topics, their implications, and how they connect to various fields. We will cover areas such as topology, numerical analysis, machine learning, and their relevance in real-world applications. Topology is the study of properties that remain invariant under continuous transformations. It focuses on the qualitative aspects of space rather than quantitative measurements. Key concepts. Open and closed sets. In topology, an open set is a collection of points where each point has a neighborhood entirely contained within the set. A closed set contains all its limit points. Homeomorphism, a continuous function between two topological spaces that has a continuous inverse. If two spaces are homomorphic, they are considered topologically equivalent. Compactness, a property of a space that generalizes the notion of closed and bounded subsets in Euclidean space. Compact spaces have important implications in analysis and topology. Applications of topology data analysis. Topological data analysis, TDA, is used to study the shape of data and extract meaningful insights, especially in high-dimensional datasets. Robotics, topology helps in motion planning by understanding configuration spaces, which represent all possible positions of a robot. Numerical analysis. Numerical analysis involves developing algorithms for approximating solutions to mathematical problems that cannot be solved analytically. Key concepts. Error analysis. Understanding how errors propagate through numerical computations is crucial for ensuring accuracy. Root-finding algorithms. Methods such as the Newton-Raphson method or bisection method are used to find roots of equations numerically. Numerical integration. Techniques like Simpson's rule or trapezoidal rule approximate the integral of functions when analytical solutions are difficult to obtain. Applications of numerical analysis engineering simulations used in finite element analysis, or FEA, for structural engineering to simulate physical phenomena. Weather forecasting. Numerical weather prediction models rely on complex algorithms to simulate atmospheric conditions. Machine learning ML, is a subset of artificial intelligence that focuses on building systems that learn from data and improve their performance over time without being explicitly programmed. Key concepts. Supervised learning involves training models on labeled data, where the algorithm learns to map inputs to outputs, for example, linear regression, decision trees. Unsupervised learning involves finding patterns in data without labeled outcomes, for example, clustering algorithms like k-means. Neural networks. Inspired by biological neural networks, these models consist of layers of interconnected nodes that can learn complex patterns from large datasets. Applications of machine learning healthcare, used for predictive analytics in patient diagnosis and treatment recommendations based on historical data. Finance. Algorithms analyze market trends for stock trading and risk management. Game theory. Game theory studies strategic interactions among rational decision makers. It provides tools for analyzing situations where individuals or groups make decisions that affect each other's outcomes. Key concepts. Nash equilibrium. A situation where no player can benefit by changing their strategy while others keep theirs unchanged. It represents a stable state in strategic interactions. Mixed strategies involves randomizing over possible actions to keep opponents uncertain about one's strategy. Applications of game theory. Economics analyzes market competition, bargaining scenarios, and auction designs. Political science models voting behavior, coalition formation, and international relations. Mathematical finance applies mathematical methods to analyze financial markets and securities. It encompasses various models used for pricing derivatives, managing risk, and optimizing investment portfolios. Key concepts. Black-Scholes model, a mathematical model for pricing options that accounts for factors like volatility and time until expiration. Portfolio theory, developed by Harry Markowitz. It focuses on maximizing returns while minimizing risk through diversification. Applications of mathematical finance: risk management. Quantitative methods assess financial risks and develop strategies to mitigate them. Algorithmic trading: mathematical models guide automated trading strategies based on market signals and statistical analysis. Conclusion: the exploration of topology, numerical analysis, machine learning, game theory, and mathematical finance highlights the diverse applications of mathematics across disciplines. Each topic enhances our understanding and provides powerful tools for solving practical problems in engineering, economics, healthcare, technology, and beyond. If there are specific areas you would like to explore further, such as applications in specific industries or deeper dives into particular mathematical theories, please let me know. Further exploration of advanced mathematical concepts and their applications. Let's continue our exploration by diving into additional advanced mathematical topics, their implications, and how they connect to various fields. We will cover areas such as differential equations, statistics in big data, cryptography, and the role of mathematics in artificial intelligence. Differential equations. Differential equations involve equations that relate a function with its derivatives. They are fundamental in modeling various physical phenomena. Key concepts. Ordinary differential equations, ODEs. Equations involving functions of a single variable and their derivatives. For example, dx plus dx dg plus y cubed. This is a first-order linear ODE, or partial differential equations, PDEs, equations involving functions of multiple variables and their partial derivatives. An example is the heat equation, ut theta 2 acted with U initial and boundary conditions. Solutions to differential equations often require specific conditions at the start, initial, or at the boundaries of the domain, boundary conditions. Applications of differential equations: physics, used to model motion, heat conduction, wave propagation, and fluid dynamics. Biology models population dynamics through logistic growth equations or predator-prey models. Statistics in big data. With the rise of big data, statistical methods have become increasingly important for analyzing large data sets. Key concepts. Descriptive statistics summarizes data through measures such as mean, median, mode, variance, and standard deviation. Inferential statistics allows conclusions to be drawn about populations based on sample data. Techniques include hypothesis testing and confidence intervals. Machine learning algorithms. Many algorithms rely on statistical principles for training models on large data sets. Applications of statistics in big data, predictive analytics, used in marketing to forecast consumer behavior based on historical data. Healthcare analytics analyzes patient data to improve treatment outcomes and operational efficiency in healthcare systems. Cryptography. Cryptography is the practice of securing communication and information through mathematical techniques. It ensures confidentiality, integrity, authentication, and non-repudiation. Key concepts. Symmetric encryption uses the same key for both encryption and decryption, for example, AES, Advanced Encryption Standard. Asymmetric encryption utilizes a pair of keys, public and private. The RSA algorithm is a well-known example where the public key encrypts data, while only the private key can decrypt it. Hash functions produce a fixed size hash value from input data of any size. Hash functions are crucial for ensuring data integrity, for example, SHA-256. Applications of cryptography secure communications ensures that messages remain confidential during transmission over insecure channels, for example, HTTPS. Digital signatures provides authentication and integrity for digital documents and transactions. Mathematics in artificial intelligence. Mathematics plays a crucial role in artificial intelligence, AI, providing the foundation for algorithms that enable machines to learn from data. Key concepts. Linear algebra, essential for understanding neural networks as they rely heavily on matrix operations. Calculus, used in optimization problems to minimize loss functions during training processes in machine learning. Probability and statistics, fundamental for making predictions based on uncertain data and for evaluating model performance. Applications of mathematics in AI natural language processing, NLP. Algorithms analyze text data using statistical methods to understand language patterns. Computer vision. Mathematical models help machines interpret visual information from the world around them. Game theory in economics. Game theory is widely applied in economics to model strategic interactions among agents, individuals or firms making decisions that affect one another. Key concepts: cooperative versus non-cooperative games. Cooperative games involve binding agreements among players, while non-cooperative games focus on individual strategies without collaboration. Repeated games. Situations where players encounter the same game multiple times, allowing for strategy evolution based on past outcomes. Applications of game theory in economics. Market competition analyzes how firms compete with one another regarding pricing strategies and product offerings. Auction theory studies bidding strategies in auctions to maximize utility or profit based on competitors' behaviors. Conclusion: the exploration of differential equations, statistics in big data, cryptography, mathematics in artificial intelligence, and game theory in economics highlights the vast applications of mathematics across various disciplines. Each topic not only enhances our understanding but also provides powerful tools for solving practical problems in fields such as engineering, finance, healthcare, technology, and social sciences. If there are specific areas you would like to explore further, such as applications in specific industries or deeper dives into particular mathematical theories, please let me know. Continuing the exploration of advanced mathematical concepts and their applications. Let's delve deeper into more advanced mathematical topics, their implications, and how they connect to various fields. We will cover areas such as stochastic processes, operations research, mathematical logic, and their relevance in real-world applications. Stochastic processes are mathematical objects that evolve over time in a probabilistic manner. They are used to model systems that exhibit randomness and uncertainty. Key concepts: random walks. A simple stochastic process where an object moves randomly in steps. For example, a stock price can be modeled as a random walk, reflecting the unpredictable nature of market movements. Markov chains, a type of stochastic process where the future state depends only on the current state and not on past states. Memoryless property. Markov chains can be discrete or continuous. Poisson processes, models. Events that occur randomly over time or space, often used in queuing theory and telecommunications. Applications of stochastic processes. Finance, used in modeling stock prices and risk assessment through models like the Black-Scholes model for option pricing. Queuing theory analyzes waiting lines in systems such as customer service centers or network data packets. Operations research, OR, is a discipline that uses advanced analytical methods to help make better decisions. It combines mathematical modeling, statistical analysis, and optimization techniques. Key concepts: linear programming, a method for optimizing a linear objective function subject to linear constraints. The simplex algorithm is commonly used for solving these problems. Integer programming, a type of linear programming where some or all variables are constrained to take integer values. This is useful in scenarios where solutions must be whole numbers, for example, scheduling. Simulation. Techniques like Monte Carlo simulation allow for modeling complex systems by generating random samples to estimate outcomes. Applications of operations research. Supply chain management optimizes logistics and inventory management to reduce costs and improve efficiency. Transportation helps design optimal routing for delivery vehicles or public transportation systems. Mathematical logic. Mathematical logic is a subfield of mathematics that uses formal logical systems to study the nature of mathematical reasoning. Key concepts: propositional logic deals with propositions that can be true or false and uses logical connectives, and Oregon not to form compound statements. Predicate logic extends propositional logic by including quantifiers, universal and existential, and predicates, allowing for more expressive statements about objects. Proof techniques. Various methods are used to establish the validity of statements, including direct proof, proof by contradiction, and induction. Applications of mathematical logic. Computer science forms the basis for algorithms, programming languages, and automated theorem proving. Philosophy, used in formalizing arguments and reasoning about mathematical truths. Graph theory. Graph theory is the study of graphs as mathematical structures used to model pairwise relationships between objects. It has applications across various fields. Key concepts: vertices and edges. A graph consists of vertices, nodes, connected by edges, lines. Graphs can be directed or undirected. Paths and cycles. A path is a sequence of edges connecting vertices. A cycle is a path that starts and ends at the same vertex without repeating edges. Connectivity. A graph is connected if there is a path between every pair of vertices. Applications of graph theory network analysis. Used in social network analysis to study relationships among individuals or organizations. Routing algorithms. Algorithms like Dijkstra's are used for finding the shortest paths in transportation networks or computer networks. Mathematics in computer science. Mathematics underpins many concepts in computer science, providing tools for algorithm design, data structures, and computational theory. Key concepts. Algorithm complexity. Big O notation describes the performance or efficiency of an algorithm in terms of time or space as input size grows. Data structures. Mathematical concepts such as trees, graphs, and hash tables are foundational for organizing and managing data efficiently. Cryptography relies on number theory and combinatorics for secure communication protocols. Applications of mathematics in computer science. Machine learning. Algorithms leverage statistical methods to learn from data patterns. Artificial intelligence, mathematical logic, and probability play crucial roles in developing intelligent systems capable of reasoning and decision-making. Conclusion. The exploration of stochastic processes, operations research, mathematical logic, graph theory, and the role of mathematics in computer science highlights the vast applications of mathematics across multiple disciplines. Each topic enhances our understanding while providing powerful tools for solving practical problems in fields such as engineering, economics, healthcare, technology, and social sciences. If there are specific areas you would like to explore further, such as applications in specific industries or deeper dives into particular mathematical theories, please let me know. Continuing the exploration of advanced mathematical concepts and their applications, let's further explore additional advanced mathematical topics, their implications, and how they connect to various fields. We will cover areas such as combinatorial optimization, mathematical modeling, numerical methods, and the role of mathematics in environmental science. Combinatorial optimization. Combinatorial optimization is a field that focuses on optimizing an objective function by selecting the best combination of discrete items from a finite set. Key concepts: NP-hard and NP-complete problems. These are classes of problems for which no known polynomial time algorithms can solve them. Examples include the traveling salesman problem, TSP, and the knapsack problem, greedy algorithms. These algorithms make a series of choices, each of which looks best at the moment, with the hope of finding a global optimum. While they work well for some problems, they do not guarantee optimal solutions for all. Dynamic programming, a method for solving complex problems by breaking them down into simpler subproblems. It is particularly useful for optimization problems where decisions depend on previous decisions. Applications of combinatorial optimization. Logistics, used to optimize routing and scheduling in supply chain management. Network design helps design efficient communication networks by optimizing connections and bandwidth usage. Mathematical modeling. Mathematical modeling involves creating abstract representations of real-world systems using mathematical language. Models can be used to simulate behaviors or predict outcomes. Key concepts: deterministic models. Models where outcomes are precisely determined by parameters, for example, population growth models. Stochastic models incorporate randomness and uncertainty, for example, stock market models. Differential equation models, often used in natural sciences to describe how systems change over time, for example, predator-prey models. Applications of mathematical modeling. Epidemiology models the spread of diseases to inform public health strategies, for example, CRO models. Economics. Economic models help forecast market trends and analyze policy impacts. Numerical methods. Numerical methods provide techniques for approximating solutions to mathematical problems that cannot be solved analytically. They are essential in various scientific computations. Key concepts: root-finding algorithms. Methods like Newton-Raphson or bisection are used to find roots of equations numerically. Numerical integration. Techniques such as Simpson's rule or the trapezoidal rule approximate the integral of functions when analytical solutions are difficult to obtain. Finite difference methods, used for solving differential equations by approximating derivatives with difference equations. Applications of numerical methods. Engineering simulations, used in finite element analysis, FEA. for structural engineering to simulate physical phenomena. Weather forecasting, numerical weather prediction models rely on complex algorithms to simulate atmospheric conditions. Mathematics in environmental science. Mathematics plays a crucial role in environmental science, helping model complex ecological systems and predict changes due to human activities or natural events. Key concepts: ecological modeling uses differential equations and statistical methods to model population dynamics, species interactions, and ecosystem changes. Climate modeling. Mathematical models simulate climate systems, incorporating variables such as temperature, humidity, and atmospheric pressure. Resource management models optimize the use of natural resources while considering sustainability and environmental impact. Applications in environmental science. Pollution modeling predicts the dispersion of pollutants in air or water bodies to assess environmental impact. Conservation biology uses mathematical models to evaluate strategies for species conservation and habitat preservation. Mathematics in social sciences. Mathematics is increasingly used in social sciences to analyze data, model behaviors, and make predictions about social phenomena. Key concepts: statistical analysis. Techniques such as regression analysis help understand relationships between variables in social research. Game theory analyzes strategic interactions among individuals or groups in various contexts, including economics and political science. Applications in social sciences. Public policy analysis uses mathematical models to evaluate the potential impacts of policy changes on society. Sociological research. Statistical methods analyze survey data to understand social trends and behaviors. Conclusion: the exploration of combinatorial optimization, mathematical modeling, numerical methods, and mathematics in environmental science, and the role of mathematics in social sciences highlights the vast applications of mathematics across multiple disciplines. Each topic enhances our understanding while providing powerful tools for solving practical problems in fields such as engineering, economics, healthcare, technology, environmental science, and social sciences. If there are specific areas you would like to explore further, such as applications in specific industries or deeper dives into particular mathematical theories, please let me know. Continuing the exploration of advanced mathematical concepts and their applications, let's delve deeper into additional advanced mathematical topics, their implications, and how they connect to various fields. We will cover areas such as topology in data science, advanced statistical methods, mathematical finance, and the role of mathematics in artificial intelligence. Topology in data science. Topology is increasingly being applied in data science, particularly in the analysis of high-dimensional data sets. Topological data analysis, TDA, provides tools for understanding the shape and structure of data. Key concepts: persistent homology, a method used to study the topological features of a space at various scales. It captures features such as connected components, holes, and voids in data. Simplicial complexes, structures that generalize graphs to higher dimensions. They are used to represent complex relationships in data. Mapper algorithm, a technique that creates a simplified representation of high-dimensional data by clustering and organizing it based on topological features. Applications of topology in data science. Biological data analysis. TDA is used to analyze complex biological structures such as protein shapes or gene expression data. Image recognition. Topological features can enhance machine learning models for image classification by providing additional structural information. Advanced statistical methods. As data becomes more complex, advanced statistical methods are required to extract meaningful insights. These methods go beyond traditional statistics to address challenges posed by big data. Key concepts: Bayesian statistics, a framework that incorporates prior knowledge into statistical analysis. It updates beliefs based on new evidence using Bayes' theorem. Multivariate analysis, techniques that analyze multiple variables simultaneously to understand relationships and patterns. For example, principal component analysis, factor analysis. Swim series analysis, methods for analyzing time-ordered data points to identify trends, seasonal patterns, and forecasting future values. For example, ARIMA models. Applications of advanced statistical methods. Econometrics uses statistical methods to analyze economic data and test hypotheses about economic theories. Healthcare analytics. Advanced statistics help in predicting patient outcomes and optimizing treatment plans based on historical health records. Mathematical finance. Mathematical finance applies mathematical methods to analyze financial markets and securities. It encompasses various models used for pricing derivatives, managing risk, and optimizing investment portfolios. Key concepts. Black-Scholes model, a mathematical model for pricing options that accounts for factors like volatility, time until expiration, and interest rates. Portfolio theory. Developed by Harry Markowitz, it focuses on maximizing returns while minimizing risk through diversification. Value at risk (VR), a statistical measure that quantifies the potential loss in value of an asset or portfolio over a defined period for a given confidence interval. Applications of mathematical finance. Risk management. Quantitative methods assess financial risks and develop strategies to mitigate them. Algorithmic trading. Mathematical models guide automated trading strategies based on market signals and statistical analysis. Mathematics in artificial intelligence. Mathematics is foundational in developing algorithms and models that enable machines to learn from data. Various mathematical disciplines contribute significantly to AI. Key concepts. Linear algebra, essential for understanding neural networks as they rely heavily on matrix operations for computations. Calculus, used in optimization problems to minimize loss functions during training processes in machine learning. Probability. And statistics, fundamental for making predictions based on uncertain data and evaluating model performance through metrics like accuracy and precision. Applications of mathematics in AI. Natural language processing, NLP. Algorithms analyze text data using statistical methods to understand language patterns and generate human-like responses. Computer vision. Mathematical models help machines interpret visual information from the world around them through techniques like convolutional neural networks, CNNs. Mathematical ethics. As mathematics increasingly influences decision-making processes in technology and society, the ethical implications of mathematical applications have come into focus. Key concepts. Algorithmic bias. The potential for algorithms to produce biased outcomes based on flawed assumptions or biased training data. Transparency and accountability. The importance of making mathematical models understandable and accountable to stakeholders affected by their decisions. Applications of mathematical ethics. Fairness in machine learning. Developing algorithms that ensure equitable treatment across different demographic groups. Data privacy. Applying mathematical principles to safeguard personal information while allowing for effective analysis. Conclusion. The exploration of topology in data science, advanced statistical methods, mathematical finance, mathematics in artificial intelligence, and mathematical ethics highlights the vast applications of mathematics across multiple disciplines. Each topic enhances our understanding while providing powerful tools for solving practical problems in fields such as engineering, economics, healthcare, technology, environmental science, social sciences, and ethics. If there are specific areas you would like to explore further, such as applications in specific industries or deeper dives into particular mathematical theories, please let me know. Continuing the exploration of advanced mathematical concepts and their applications, let's delve deeper into additional advanced mathematical topics, their implications, and how they connect to various fields. We will cover areas such as quantum mathematics, mathematical biology, operations research and logistics, and the role of mathematics in climate modeling. Quantum mathematics. Quantum mathematics deals with the mathematical foundations of quantum mechanics, which describes the behavior of matter and energy at very small scales. Key concepts. Hilbert spaces. A fundamental concept in quantum mechanics, Hilbert spaces are complete vector spaces that provide the framework for quantum states. They allow for the representation of quantum states as vectors. Operators in quantum mechanics, physical observables such as position and momentum, are represented by operators acting on Hilbert spaces. The eigenvalues of these operators correspond to measurable quantities. Quantum entanglement, a phenomenon where quantum particles become interconnected such that the state of one particle instantly influences the state of another, regardless of distance. Applications of quantum mathematics. Quantum computing utilizes principles of quantum mechanics to perform computations much faster than classical computers for certain problems, for example, factoring large numbers. Quantum cryptography provides secure communication methods based on the principles of quantum mechanics, ensuring that any attempt to eavesdrop can be detected. Mathematical biology. Mathematical biology applies mathematical techniques to understand biological systems and phenomena. It often involves modeling biological processes through differential equations and statistical methods. Key concepts. Population dynamics, models that describe how populations change over time due to births, deaths, immigration, and emigration. The logistic growth model is a common example. Epidemiological models use differential equations to model the spread of diseases within populations, for example, SRR models. These models help predict disease outbreaks and evaluate control strategies. Phylogenetics, the study of evolutionary relationships among biological species using statistical methods to analyze genetic data. Applications of mathematical biology. Conservation biology. Models help assess the viability of species populations and inform conservation strategies. Drug development. Mathematical models can predict how drugs interact with biological systems, aiding in the design of effective treatments. Operations research. In logistics, operations research, OR, applies mathematical methods to decision-making processes in logistics and supply chain management, optimizing efficiency and reducing costs. Key concepts. Linear programming. A method for optimizing a linear objective function subject to linear constraints, commonly used in resource allocation problems. Network flow problems involves optimizing flows through a network to minimize costs or maximize efficiency, for example, of transportation networks. Simulation modeling. Techniques like Monte Carlo simulation are used to model complex systems with uncertainty and evaluate different scenarios. Applications of operations research in logistics, supply chain optimization, or techniques help streamline supply chains by optimizing inventory levels, transportation routes, and production schedules. Warehouse management. Models assist in designing efficient warehouse layouts and managing stock levels effectively. Mathematics in climate modeling. Mathematics plays a crucial role in climate science by providing tools for modeling complex climate systems and predicting future climate changes. Key concepts. Differential equations, used to model physical processes governing climate dynamics, including heat transfer and fluid motion in the atmosphere and oceans. Coupled models integrate various components, atmosphere, oceans, land surface, into a single framework for comprehensive climate simulations. Statistical downscaling, techniques that refine coarse climate model outputs to provide localized predictions relevant for impact assessments. Applications of mathematics in climate modeling. Climate change. Projections. Mathematical models simulate future climate scenarios based on different greenhouse gas emission pathways. Impact assessment. Models evaluate potential impacts of climate change on ecosystems, agriculture, water resources, and human health. Mathematics in finance. Mathematics is fundamental in finance for modeling markets, assessing risks, and optimizing investment strategies. Key concepts. Stochastic calculus, a branch of mathematics that deals with processes involving randomness, essential for modeling financial markets, for example, Ito calculus. Option pricing models. Mathematical frameworks like Black-Scholes provide methods for pricing financial derivatives based on underlying assets' behavior. Risk assessment models. Quantitative methods assess financial risks associated with investments or portfolios, for example, value at risk. Applications of mathematics in finance portfolio optimization. Mathematical models help investors construct portfolios that maximize returns while minimizing risk based on historical data. Algorithmic trading uses mathematical algorithms to automate trading decisions based on market data analysis. Conclusion. The exploration of quantum mathematics, mathematical biology, operations, research in logistics, mathematics in climate modeling, and mathematics in finance highlights the vast applications of mathematics across multiple disciplines. Each topic enhances our understanding while providing powerful tools for solving practical problems in fields such as engineering, economics, healthcare, technology, environmental science, social sciences, and finance. If there are specific areas you would like to explore further, such as applications in specific industries or deeper dives into particular mathematical theories, please let me know. Continuing the exploration of advanced mathematical concepts and their applications, let's delve deeper into additional advanced mathematical topics, their implications, and how they connect to various fields. We will cover areas such as information theory, mathematical physics, game theory applications, and the role of mathematics in cybersecurity. Information theory. Information theory is a branch of applied mathematics and electrical engineering that deals with the quantification, storage, and communication of information. Key concepts. Entropy, a measure of uncertainty or randomness in a set of data. In information theory, it quantifies the amount of information produced by a stochastic source of data. Higher entropy indicates more unpredictability. Mutual information measures the amount of information that one random variable contains about another random variable. It is used to assess the dependency between variables. Shannon's theorem establishes the maximum rate at which information can be transmitted over a communication channel without error, known as the channel capacity. Applications of information theory. Data compression. Techniques like Huffman coding and Lempel-Ziv-Welch LZW. Compression reduce the size of data for efficient storage and transmission. Error detection and correction. Codes are designed to detect and correct errors in data transmission, for example, Reed-Solomon codes. Mathematical physics. Mathematical physics applies rigorous mathematical methods to solve problems in physics and develop theoretical frameworks. Key concepts: differential equations, used extensively to describe physical phenomena such as Newton's laws of motion or Maxwell's equations in electromagnetism. Group theory studies symmetries in physical systems, playing a crucial role in quantum mechanics and particle physics. Statistical mechanics connects microscopic properties of particles with macroscopic observable properties, for example, temperature, pressure, using probability theory. Applications of mathematical physics. Quantum field theory combines classical field theory with quantum mechanics to describe fundamental forces and particles. General relativity uses differential geometry to describe gravitation as the curvature of space-time caused by mass. Game theory applications. Game theory analyzes strategic interactions among rational decision-makers. It has applications across various fields beyond economics. Key concepts: cooperative versus non-cooperative games. Cooperative games involve binding agreements among players, while non-cooperative games focus on individual strategies without collaboration. Evolutionary game theory studies strategies in biological contexts where individuals compete for resources or mates, incorporating concepts from evolutionary biology. Applications of game theory. Political science models voting behavior, coalition formation, and negotiation strategies among political entities. Biology analyzes evolutionary strategies among species competing for survival, for example, hawk-dove game. Mathematics in cybersecurity. Mathematics plays a critical role in ensuring the security of digital information through various cryptographic techniques and protocols. Key concepts: public key cryptography utilizes asymmetric encryption methods where two keys, public and private, are used for secure communication, for example, RSA algorithm. Hash functions produce unique fixed-size outputs from variable-size inputs, ensuring data integrity by detecting changes, for example, SHA-256. Digital signatures provide authentication and non-repudiation for digital messages or documents using cryptographic techniques. Applications of mathematics in cybersecurity. Secure communications ensures that sensitive information transmitted over networks remains confidential through encryption. Intrusion detection systems use statistical analysis and machine learning algorithms to identify unusual patterns that may indicate security breaches. Mathematics in social sciences. Mathematics is increasingly used in social sciences to analyze data, model behaviors, and make predictions about social phenomena. Key concepts: statistical methods. Techniques such as regression analysis help understand relationships between variables in social research. Network analysis studies relationships within social networks using graph theory to understand connectivity and influence among individuals or groups. Applications in social sciences. Public policy analysis uses mathematical models to evaluate potential impacts of policy changes on society. Sociological research. Statistical methods analyze survey data to understand social trends and behaviors. Conclusion: the exploration of information theory, mathematical physics, game theory applications, mathematics in cybersecurity, and mathematics in social sciences highlights the vast applications of mathematics across multiple disciplines. Each topic enhances our understanding while providing powerful tools for solving practical problems in fields such as engineering, economics, healthcare, technology, environmental science, social sciences, finance, and security. If there are specific areas you would like to explore further, such as applications in specific industries or deeper dives into particular mathematical theories, please let me know. Continuing the exploration of advanced mathematical concepts and their applications. Let's delve deeper into additional advanced mathematical topics, their implications, and how they connect to various fields. We will cover areas such as fractal geometry, mathematical modeling in epidemiology, the role of mathematics in artificial intelligence, and advanced numerical methods. Fractal geometry studies complex structures that exhibit self-similarity across different scales. Fractals are often used to model natural phenomena that do not conform to traditional geometric shapes. Key concepts. Self-similarity, a property where a structure looks similar at different scales. For example, the coastline of a landmass appears jagged at both the macro and micro levels. Fractal dimension, a measure that quantifies how a fractal scales differently than traditional geometric shapes. It can be non-integer, indicating complexity beyond one-dimensional lines or two-dimensional surfaces. Iterated function systems, IFS, a method for constructing fractals using a set of contraction mappings. The famous Sierpinski triangle is an example of a fractal generated by IFS. Applications of fractal geometry, natural phenomena. Fractals are used to model irregular shapes in nature, such as clouds, mountains, and coastlines. Computer graphics. Fractal algorithms generate realistic textures and landscapes in computer-generated imagery, CGI. Mathematical modeling in epidemiology. Mathematical modeling plays a crucial role in understanding and predicting the spread of infectious diseases. Models help public health officials make informed decisions about interventions. Key concepts. SIR model, a compartmental model that divides the population into three categories: susceptible, S, infected, I, and recovered, R. The model uses differential equations to describe the transition between these states. Basic reproduction number, RRO, a key parameter that indicates how contagious an infectious disease is. If RO1, the disease can spread. If RO1, it will eventually die out. Agent-based models simulate interactions of individuals within a population to assess how disease spreads based on individual behavior and characteristics. Applications of mathematical modeling in epidemiology, pandemic response. Models help predict the impact of interventions such as vaccination campaigns or social distancing measures during outbreaks, for example, COVID-19 modeling. Resource allocation helps determine optimal allocation of medical resources during health crises. The role of mathematics in artificial intelligence mathematics is foundational in developing algorithms and models that enable machines to learn from data. Various mathematical disciplines contribute significantly to AI development. Key concepts: linear algebra, essential for understanding neural networks as they rely heavily on matrix operations for computations. Calculus, used in optimization problems to minimize loss functions during training processes in machine learning. Probability and statistics, fundamental for making predictions based on uncertain data and evaluating model performance through metrics like accuracy and precision. Applications of mathematics in AI deep learning utilizes complex neural networks with multiple layers to learn hierarchical representations of data. Natural language processing, NLP. Algorithms analyze text data using statistical methods to understand language patterns and generate human-like responses. Advanced numerical methods. Numerical methods provide techniques for approximating solutions to mathematical problems that cannot be solved analytically. They are essential in various scientific computations. Key concepts: finite element method, FEM, a numerical technique for finding approximate solutions to boundary value problems for partial differential equations. It is widely used in engineering for structural analysis. Spectral methods, techniques that approximate solutions by expanding them in terms of eigenfunctions of differential operators. They are particularly effective for problems with smooth solutions. Monte Carlo methods, a class of algorithms that rely on repeated random sampling to obtain numerical results, often used for estimating integrals or simulating physical systems. Applications of advanced numerical methods, engineering simulations, used extensively in finite element analysis, FEA, for structural engineering to simulate physical phenomena. Financial modeling, Monte Carlo simulations are employed to assess risk and forecast financial outcomes based on uncertain variables. Mathematics in robotics. Mathematics is integral to robotics, providing the framework for modeling robot motion, perception, and decision-making processes. Key concepts. Kinematics, the study of motion without considering forces. Kinematic equations describe how robots move through space. Control theory involves designing controllers that manage the behavior of dynamic systems, for example, PID controllers. Path planning algorithms. Algorithms like A** or Dijkstra's are used to determine optimal paths for robots navigating environments. Applications of mathematics in robotics. Autonomous vehicles. Mathematical models enable self-driving cars to navigate roads safely by predicting other vehicles' movements. Industrial automation. Robots use mathematical algorithms for tasks such as assembly line work or material handling. Conclusion. The exploration of fractal geometry, mathematical modeling in epidemiology, the role of mathematics in artificial intelligence, advanced numerical methods, and mathematics in robotics highlights the vast applications of mathematics across multiple disciplines. Each topic enhances our understanding while providing powerful tools for solving practical problems in fields such as engineering, healthcare, technology, environmental science, social sciences, finance, and more. If there are specific areas you would like to explore further, such as applications in specific industries or deeper dives into particular mathematical theories, please let me know. Continuing the exploration of advanced mathematical concepts and their applications, let's delve deeper into additional advanced mathematical topics, their implications, and how they connect to various fields. We will cover areas such as topology in data analysis, the mathematics of networks, mathematical finance, and the role of mathematics in climate science. Topology in data analysis. Topology has become increasingly relevant in data analysis, particularly through the field of topological data analysis, TDA. TDA provides tools for understanding the shape and structure of data, especially in high-dimensional spaces. Key concepts. Persistent homology, a method used to study the topological features of a space at different scales. It captures features such as connected components, holes, and voids in data across various resolutions. Simplicial complexes, structures that generalize graphs to higher dimensions. They're used to represent complex relationships in data and help visualize multidimensional data sets. Mapper algorithm, a technique that creates a simplified representation of high-dimensional data by clustering and organizing it based on topological features. Applications of topology in data analysis. Biological data. TDA is used to analyze complex biological structures such as protein shapes or gene expression data, providing insights into their functional properties. Image analysis. Topological features can enhance machine learning models for image classification by providing additional structural information beyond pixel intensity. The mathematics of networks. Network theory studies the relationships between interconnected entities. It has applications across various fields, including sociology, biology, computer science, and transportation. Key concepts. Graph theory. The mathematical study of graphs, which are composed of vertices, nodes, connected by edges, links. Graphs can be directed or undirected and weighted or unweighted. Centrality measures, metrics that identify the most important vertices within a network. Common measures include degree centrality, betweenness centrality, and closeness centrality. Community detection, algorithms that identify clusters or groups within networks where nodes are more densely connected to each other than to the rest of the network. Applications of network theory. Social network analysis, used to study relationships among individuals or groups, revealing patterns of influence and connectivity. Biological networks models, interactions among proteins, genes, or metabolic pathways to understand cellular functions and disease mechanisms. Mathematical finance. Mathematical finance applies mathematical methods to analyze financial markets and securities. It encompasses various models used for pricing derivatives, managing risk, and optimizing investment portfolios. Key concepts. Black-Scholes model, a mathematical model for pricing options that accounts for factors like volatility and time until expiration. It provides a theoretical estimate for the price of European-style options. Portfolio theory developed by Harry Markowitz, it focuses on maximizing returns while minimizing risk through diversification. The efficient frontier represents optimal portfolios that offer the highest expected return for a given level of risk. Risk management models. Quantitative methods assess financial risks associated with investments or portfolios, for example, value at risk. Applications of mathematical finance. Option pricing. Mathematical models help traders determine fair prices for options based on market conditions. Algorithmic trading uses mathematical algorithms to automate trading decisions based on market data analysis and statistical patterns. Mathematics in climate science. Mathematics plays a crucial role in climate science by providing tools for modeling complex climate systems and predicting future climate changes. Key concepts. Differential equations, used to model physical processes governing climate dynamics, including heat transfer and fluid motion in the atmosphere and oceans. Coupled models integrate various components, atmosphere, oceans, land surface, into a single framework for comprehensive climate simulations. Statistical downscaling, techniques that refine coarse climate model outputs to provide localized predictions relevant for impact assessments. Applications of mathematics in climate science. Climate change projections. Mathematical models simulate future climate scenarios based on different greenhouse gas emission pathways. Impact assessment. Models evaluate potential impacts of climate change on ecosystems, agriculture, water resources, and human health. Mathematics in operations research. Operations research, OR, employs mathematical techniques to optimize decision-making processes across various industries. Key concepts. Linear programming, a method for optimizing a linear objective function subject to linear constraints. The simplex algorithm is commonly used for solving these problems. Integer programming, a type of linear programming where some or all variables are constrained to take integer values. This is useful in scenarios where solutions must be whole numbers, for example, scheduling. Simulation modeling. Techniques like Monte Carlo simulation allow for modeling complex systems with uncertainty and evaluating different scenarios. Applications of operations research. Supply chain management, or techniques help streamline supply chains by optimizing inventory levels, transportation routes, and production schedules. Transportation logistics. Models assist in designing efficient routing for delivery vehicles or public transportation systems. Conclusion. The exploration of topology and data analysis, the mathematics of networks, mathematical finance, mathematics in climate science, and mathematics in operations research highlights the vast applications of mathematics across multiple disciplines. Each topic enhances our understanding while providing powerful tools for solving practical problems in fields such as engineering, economics, healthcare, technology, environmental science, social sciences, finance, and more. If there are specific areas you would like to explore further, such as applications in specific industries or deeper dives into particular mathematical theories, please let me know. Continuing the exploration of advanced mathematical concepts and their applications, let's delve deeper into additional advanced mathematical topics, their implications, and how they connect to various fields. We will cover areas such as chaos theory, mathematical modeling in economics, the role of mathematics in artificial intelligence, and advanced statistical methods. Chaos theory studies complex systems that are highly sensitive to initial conditions, leading to seemingly random behavior despite being deterministic. This field has applications across various disciplines. Key concepts. Sensitivity to initial conditions, often illustrated by the butterfly effect, where small changes in initial conditions can lead to vastly different outcomes in a system. Strange attractors, patterns that emerge in chaotic systems representing stable states toward which a system tends to evolve over time. Bifurcation theory studies how changes in parameters can cause sudden shifts in the behavior of a system, leading to different types of dynamics. Applications of chaos theory. Weather forecasting. Chaos theory plays a crucial role in understanding and predicting weather patterns due to the complex interactions within the atmosphere. Economics. Economic models can exhibit chaotic behavior influencing market predictions and financial strategies. Mathematical modeling in economics. Mathematical modeling is essential in economics for analyzing and predicting economic behavior and trends. It helps economists understand complex relationships between variables. Key concepts. Supply and demand models. These models describe how prices are determined in a market based on the relationship between supply and demand. Game theory in economics, used to model strategic interactions among firms or individuals, helping to predict outcomes in competitive markets. Dynamic systems. Models that describe how economic variables evolve over time, often using differential equations to analyze growth rates and cycles. Applications of mathematical modeling in economics. Macroeconomic forecasting. Models help predict economic indicators such as GDP growth, inflation rates, and unemployment. Policy analysis. Mathematical models evaluate the potential impacts of fiscal or monetary policy changes on the economy. The role of mathematics in artificial intelligence. Mathematics is foundational in developing algorithms and models that enable machines to learn from data. Various mathematical disciplines contribute significantly to AI development. Key concepts. Linear algebra, essential for understanding neural networks as they rely heavily on matrix operations for computations. Calculus, used in optimization problems to minimize loss. Functions during training processes in machine learning. Probability and statistics, fundamental for making predictions based on uncertain data and evaluating model performance through metrics like accuracy and precision. Applications of mathematics in AI deep learning. Utilizes complex neural networks with multiple layers to learn hierarchical representations of data. Natural language processing, NLP. Algorithms analyze text data using statistical methods to understand language patterns and generate human-like responses. Advanced statistical methods. As data becomes more complex, advanced statistical methods are required to extract meaningful insights. These methods go beyond traditional statistics to address challenges posed by big data. Key concepts. Bayesian statistics, a framework that incorporates prior knowledge into statistical analysis. It updates beliefs based on new evidence using Bayes' theorem. Multivariate analysis, techniques that analyze multiple variables simultaneously to understand relationships and patterns. For example, principal component analysis, factor analysis. Time series analysis, methods for analyzing time-ordered data. Points to identify trends, seasonal patterns, and forecasting future values, for example, ARIMA models. Applications of advanced statistical methods. Econometrics uses statistical methods to analyze economic data and test hypotheses about economic theories. Healthcare analytics, advanced statistics help in predicting patient outcomes and optimizing treatment plans based on historical health records. Mathematics in cryptography. Mathematics is fundamental in ensuring secure communication through cryptography. Various mathematical principles underpin modern cryptographic techniques. Key concepts. Symmetric encryption uses the same key for both encryption and decryption, for example, AES, Advanced Encryption Standard. Asymmetric encryption utilizes a pair of keys, public and private, for secure communication, for example, RSA algorithm. Hash functions produce a fixed size hash value from input data of any size. Hash functions are crucial for ensuring data integrity, for example, SHA-256. Applications of mathematics in cryptography. Secure communications ensures that messages remain confidential during transmission over insecure channels, for example, HTTPS. Digital signatures provides authentication and integrity for digital documents and transactions using cryptographic techniques. Conclusion. The exploration of chaos theory, mathematical modeling in economics, the role of mathematics in artificial intelligence, advanced statistical methods, and mathematics in cryptography highlights the vast applications of mathematics across multiple disciplines. Each topic enhances our understanding while providing powerful tools for solving practical problems in fields such as engineering, economics, healthcare, technology, environmental science, social sciences, finance, security, and more. If there are specific areas you would like to explore further, such as applications in specific industries or deeper dives into particular mathematical theories, please let me know. Certainly. Here's a comprehensive summary of all the advanced mathematical concepts and their applications that we have discussed. Summary of mathematical concepts and applications. Unique numbers and their constraints. Definition of unique numbers and examples in real life. The significance of the number 1 as a foundational element in mathematics. Basic foundations of numbers. Concatenation of numbers and their properties, exploring arithmetic sequences and geometric sequences. Fibonacci numbers, the Fibonacci sequence and its appearance in nature. The relationship between Fibonacci numbers and the golden ratio. Prime numbers definition and properties of prime numbers. Applications of prime numbers in cryptography. Modular arithmetic concepts and applications in computer science and cryptography. Graph theory, study of graphs, vertices, edges, paths, and cycles. Applications in social network analysis and routing algorithms. linear algebra vectors, matrices, eigenvalues, and eigenvectors. Applications in computer graphics and machine learning, statistics, descriptive versus inferential statistics, applications in healthcare, marketing, and social sciences. Probability theory. Random variables, probability distributions, expectation and variance, applications in finance, risk assessment and decision-making. Game theory, Nash equilibrium, cooperative versus non-cooperative games, applications in economics, political science and biology. Differential equations, ordinary versus partial differential equations, applications in physics, biology and engineering. Numerical methods, techniques for approximating solutions to mathematical problems. Applications in simulations, engineering analysis and financial modeling, topology, open-closed sets, homomorphism, compactness, applications in data analysis, topological data analysis and robotics, mathematical modeling, creating abstract representations of real-world systems, applications in epidemiology, disease spread models and environmental science, mathematics in artificial intelligence, role of linear algebra, calculus, probability and statistics. Applications in machine learning, natural language processing and computer vision. Operations research, techniques for optimizing decision-making processes. Applications in logistics, supply chain management and transportation. Fractal geometry, self-similarity and fractal dimension. Applications in modeling natural phenomena and computer graphics. Chaos theory, sensitivity to initial conditions and strange attractors. Applications in weather forecasting and economic modeling, mathematical finance, Black-Scholes model for option pricing, portfolio theory for optimizing investment strategies, information theory, entropy, mutual information, Shannon's theorem, applications in data compression and error detection correction, mathematics in cybersecurity, public key cryptography, hash functions, digital signatures, ensuring secure communications over networks. Mathematics in climate science, modeling climate systems using differential equations, predicting climate change impacts through simulations. Mathematical biology, population dynamics models, for example, SIR models. Applications in conservation biology and drug development. The mathematics of network centrality measures and community detection. Applications in social networks and biological systems. Advanced statistical methods, Bayesian statistics, multivariate analysis, time series analysis. Applications in econometrics and healthcare analytics. This summary encapsulates the breadth of our discussions on various mathematical concepts along with their applications across different fields. If there are specific topics you would like to explore further, or if you have any new areas of interest to discuss, please let me know. Section 6: Statistics and Probability. Making sense of uncertainty. In a world characterized by uncertainty, statistics and probability provide essential tools for making informed decisions and navigating the complexities of random events. These disciplines are not just for scientists or mathematicians, they are integral to our daily lives. From weather forecasting to financial modeling, these mathematical disciplines help us quantify risk, analyze trends, and make predictions based on data. For instance, meteorologists use statistical models to predict weather patterns, while financial analysts rely on probability to forecast market trends. Statistics deals with the collection, organization, analysis, interpretation, and presentation of data. It involves gathering data from various sources, organizing it in a meaningful way, and then analyzing it to draw conclusions. It provides methods for summarizing data, identifying patterns, and drawing inferences about populations based on samples. This is crucial in fields like medicine, where researchers use statistics to determine the effectiveness of new treatments. Probability, on the other hand, deals with the likelihood of events occurring, quantifying uncertainty, and providing a framework for decision-making under uncertainty. Whether it's rolling dice or predicting stock market fluctuations, probability helps us understand the chances of different outcomes. In everyday life, we encounter statistics and probability in various forms. When we make decisions, whether it's choosing a product in a supermarket or planning a family vacation, we often rely on these principles, even if subconsciously. When we check the weather forecast, we rely on statistical models that analyze historical weather patterns and current atmospheric conditions to predict the likelihood of rain or sunshine. This helps us decide whether to carry an umbrella or plan an outdoor event. When we invest in the stock market, we rely on probability theory to assess the risks and potential returns associated with different investment options. Understanding these concepts can help us make more informed financial decisions. By understanding the principles of statistics and probability, we can become more informed consumers of information, make better decisions in our personal and professional lives, and navigate the uncertainties of a complex world with greater confidence. These tools empower us to interpret data critically and make choices that are backed by solid evidence.